I'll let Adam go have it from there.
Great. Well, I wanted to echo Lanny's sentiment. We're very excited today to do a technical deep dive into CO2 injection. It is a very hot topic in both climate and energy circles. It is a technology that is only going to grow in its use all over the country and the world. And so the more that we all know about how it actually works, the better we can regulate it for safety, efficiency, and effectiveness. And I can't thank enough Chuck and Al for putting this on for us today, and Lanny and Amy and Bay for organizing it and running it with their usual flair.
Okay, I'm going to introduce Chuck now. Chuck, you're going to turn on your, you can turn your video on if you want. Chuck Fox is the CEO and founder of Windy Cove Energy, which developed oil and gas projects in the horizontal San Andres play in the Permian Basin. Windy Cove is now pursuing other opportunities. Previously, Mr. Fox, Chuck, was the Vice President of Operations Engineering at Kinder Morgan CO2 Company. He was responsible for operating 1.2 BCF per day, which was produced out of McElma Dome and Doe Canyon CO2 source fields. Over 1,000 miles of CO2 pipe and crude oil pipelines, and he operated Sackrock, Yates, and the Katz oil fields, where we producing about 50,000 barrels of oil per day, and still many of those are still producing. Company went from zero oil production to become the second largest oil producer in Texas, Kinder Morgan. Prior to joining Kinder Morgan, Mr. Fox worked for Shell Oil Company and various domestic and international assignments. He actually hired me into Shell. So he's Mr. Fox is co-author of the Society of Petroleum Engineers monograph, Practical Aspects of CO2 Flooding, which is why I know he will do a great job on this. He is also the SB Distinguished Lecturer, and he's going to give you part of that lecture, I believe. He holds a BS in Mechanical Engineering from Rice University and an MS in Petroleum Engineering from Stanford University. He is professional engineer registered in New Mexico and Texas. Go ahead, Chuck, you have it.
Well, thanks a lot, Lanny. And let me just jump right into this. I'm surprised that there's more than 250 people that are interested in this. And thank you very much for being here. I really enjoy this subject, and I hope my enthusiasm comes across today. And there, okay. So I'm making the assumption that most of the people here are not really going to do this technology or actually make all the calculations themselves. There we go. So I'm just going to go over the basics here. I hope we understand the basics of CO2 flooding and related techniques of carbon capture. We just touch on transportation, and then we look at carbon storage, because that's ultimately what we're talking about here. We're going to look at the regulatory scheme, and I'm a little concerned about this because I know there's people here from the EPA that worked on this and got all the regulations going, and some of the people are in the various states that actually have gotten primacy, but maybe you'll straighten me out when I get done with that section. And this is something here, I'm going to go over the economics of CO2 flooding and how it relates to CO2 price requirements and capture costs, because that has to do with why we're not seeing more of it up to this point. And then there's some basic monitoring strategies for both EOR and CCS that we would engage in. This next slide is simply an outline of what we're doing, starting with an introduction, then into reservoir technology, and then the other pieces of CO2 flooding, well-designed surface facilities and operations. And that gives a background for where the regulations come. I'm going to look at carbon balance. And why are we doing this? Does this make any sense at all? I mean, how much does it take to put CO2 in the ground? I mean, how much carbon do you emit while you put CO2 in the ground? Does this make any sense at all? We'll look at screening and economics. And then some I don't know much about, and that's why Al's here. He's going to talk about 45Q tax credits, which I think are key in getting a lot of projects over the hump. Then we'll look at other storage options, and then capture, because you got to capture it first and then transport it. And then a very short section on really just a conclusion on fitting it all together. Lanny went over all this, and I have to ask if I look like this person in the picture. I don't know. I don't know if I can ever recover that, if I shave off the beard, if that would return or not, but we'll go on. All this is just to say that hopefully I know what I'm talking about. So what is carbon storage? I mean, that's really what we're heading for. And I have a couple definitions. The first one is from the Carbon Sequestration Research and Development section of the U.S. Department of Energy. And it says carbon storage can be defined as the capture and secure storage of carbon that would otherwise be emitted or remain in the atmosphere. And the idea is to, one, keep emissions produced by human activities from reaching the atmosphere by capturing, diverting them to secure storage, or to remove carbon from the atmosphere by various means and store it. Okay, so that's one definition. And CO2 storage is the process of capturing anthropogenic CO2 emitted from the combustion of fossil fuels or other means. There you can make it through industrial processes, and isolating it underground so it doesn't enter the atmosphere. And it's an attractive option for mitigating climate change. And the three parts here are capturing the CO2 from industrial or power plant emissions, transporting it to storage sites by pipeline, tank, or ship, and injecting it in the geosphere. And I'm not going to talk about tankers or ships, but I will talk about pipelines. So, so then what is CCUS? Because we talked about CCS, and now we're talking about CCUS, and it is the addition of the word utilization for the idea that, hey, well, maybe we can make some money out of this and offset the cost of storage and help pay for it. And these technologies involve the capture of carbon dioxide, again, from fuel combustion or industrial sources, transportation again, and its use as a resource to create valuable products or services, and or its permanent storage. And in this particular definition, it seems like it allows for CO2 storage in the reservoir. And maybe that's not utilization, but utilization just could be a part of this. And you could use CO2 to make other substances like plastics, concrete, and biofuels. A lot of people working on that. But what we're going to talk about is the utilization of CO2 to produce oil, or just to store it directly into the reservoir without producing the oil. So that's where we are going. And again, as part of the introduction, so taking a look at the CO2 EOR, and I say the CCUS infrastructure in the United States. And it is, there's over 250,000 barrels a day were produced due to CO2 injection in 2014. And that's the last date that there was a survey done. What you see is most of the infrastructure is in West Texas and the Rocky Mountains. There's some other pieces in the Midwest, or not Midwest, mid-continent around Oklahoma, and something down in the Mississippi and the Gulf Coast. I'll say that most of the CO2 that's used for enhanced oil recovery comes from the underground. It's not really a anthropogenic source. It comes from an underground source of CO2 brought to the surface, pipelines put back in the ground. And so that's really not addressing the climate issue. It's not hurting the climate issue because the CO2 goes back in the ground, but you're really not a net negative at that point. And again, as part of the introduction, we're going to go into this much deeper, but just to have an idea, what we're talking about is this CO2 flood schematic. And the common practice here is to inject CO2 into an oil reservoir that's amenable to miscible CO2 flooding. We'll talk about that word miscible in a minute. In these 5, 7, or 9 spot well patterns, that's just like the 5 spot looks like a checkerboard, and using some water alternating gas ratio. And in the above schematic, it's a vertical cross section of the reservoir from a CO2 injection well or a production well. And it shows what might be going on in the reservoir. And if you move from left to right, in the injection well, a water slug is being injected. And then in front of that, as we go to the right, you have a CO2 slug that was injected before that, and a water slug going again that was injected before that. In front of that's another CO2 slug. And then finally, something different's happening. It's this miscible zone where the injected CO2 has developed miscibility by multiple contacts with the in situ oil. And we'll go into that in the next section. And in front of that, finally, we get an oil bank, this high saturation oil zone that's being formed by this miscible zone that's being flushed out or pushed out in the reservoir. And so why are we doing all this? Well, you expect when you go into this, and you make calculations, but you expect to increase recovery by 8 to 15% of the original oil in place. And after a water flood, you may have only gotten 35% of the original oil in place out. So that's an additional resource and your additional recovery that you're looking for. So going on to the history of CO2 flooding, kind of hit this, but well, how did we get where we were or where we are? If you look at this, in 1952, there was a patent was issued for an oil recovery method with CO2. And when people look back on that, say, well, this person missed the mark. This really wasn't going to work like they thought, but the guy got a patent. But laboratory research was taken on by the major oil companies in the 50s and 60s, and they published that. And that was enough to encourage operators to initiate CO2 EOR projects after the 1973 oil embargo. And the basic science of miscible flooding was in place by the time the SPE, the Society of Petroleum Engineers, published miscible displacement monograph in 1983. And then there was enough field experience gained over the next 2 decades for the SPE to publish practical aspects of CO2 flooding, the monograph that came out in 2002. And I don't think any library is, complete without that book. And I say that knowing that I was one of the 4 co-authors, and so I get a quarter of the revenue. So every time you buy a book, I think I get $3.50. So please, I still have a kid in college, so please go buy that. So the beginnings began. CO2 flooding began in earnest in January 1972 when Chevron began injection at the Sack Rock oil field. We're going to talk a lot more about that through the day, but that is in West Texas, and Shell soon followed at North Cross, and that was on the same pipeline. They built it together. And 2 years later, a small company, Orla Petco, began injection at 2 Freds. And in all these cases, this was anthropogenic CO2. CO2 was separated from natural gas stream and was vented at these plants. I mean, then in the Val Verde Basin, the natural gas has quite a lot of CO2 in it naturally. And in order to get that ready for sale into the interstate pipeline system, they had to take the CO2 out. And so they knew that there was a source there, and the CO2 was captured, dehydrated, and compressed. And it was sent to Sac Rock and North Cross in two threads, and they thought it worked well enough. And that initial success and the energy crisis, it led to search for more and larger CO2 sources to expand CO2 flooding, because there wasn't enough CO2 to do all the fields that were amenable to CO2 flooding. And then the major oil companies, they identified these major sources of CO2, and they built them. They developed these sources at McElmo Dome, Sheep Mountain, Bravo Dome, that's in Colorado and northeastern New Mexico, Jackson Dome in Mississippi, and they built these pipelines. And these were all underground sources. But they also, at the time, there was LaBarge that was developed. The CO2 was captured up there. There was the Great Plains Gasification Plant in North Dakota. That came a little later, but it captured the CO2 out of a plant. And there were some ammonia plants in the panhandle of Texas and in Oklahoma that were hooked up. An interesting thing to comment on LaBarge, it's an underground source of CO2 like the others, but there's a fair amount of helium that comes up with it, and it produces 30 to 40% of the world's helium. So unlike the other sources like McElmo Dome, this is really a true anthropogenic source where you're producing a product that's vital for the world. Then the oil price dropped in '86, and that really stalled everything. There was a number of projects that kept rolling out because I guess they'd gone too far with them. But so the number of projects increased from 3 in 1974 to 29 in 1986 and 39 in 1994. And I'm not sure those companies really wanted to keep going when they kept developing those other floods from 74 to 86. I'm sorry, from 29 in 86 to 39 in 94. But then in 65 and 2000, so they kept going. This thing really did have legs, at least in the United States. And so by 2000, there seemed to be another chance for the industry to catch its breath. At 25 years of CO2 flood experience, the technical risks were thought to be well known. And the number of projects doubled from 2000 to 2014, but these projects weren't as large as those started in the 1980s. But they could be additional projects because the larger oil fields had paid for the first infrastructure. And I think that might be the case for this carbon capture and storage, is that the oil flooding has paid for the pipeline infrastructure that you can now use for CCUS. There's not been a single project after 2014. We'll talk about the economics. You'll see why. And a couple questions: is the industry going to sanction long-term projects while the memory of price volatility is remains? I think the industry got very happy drilling shale wells, although things didn't turn out very well, but at least they get their payback a lot faster than a CO2 flood. And have all the good CO2 floods been done? There was a lot of effort finding them. What's left? But the U.S. isn't the only place where there's been CO2 flooding. Canada, there's been at least 6 floods. The largest is Weyburn and Mydale. There's different parts of the field or different nomenclature. And they use CO2 captured from the Great Plains coal gasification plant in North Dakota. And that was a child of the energy crisis. It got sanctioned, I think, in the 70s. It finally went into service, I think in 1986. They gasify coal, and interesting, a byproduct is nearly pure CO2. I say nearly pure, it has 4% hydrogen sulfide. So that's kind of dangerous, but that it can be handled, and the CO2 is sent up to Canada. In Trinidad, there were 5 immiscible floods. We'll talk about immiscibility and immiscibility later. And they were sourced from a refinery. And in refineries, there are some point sources of nearly pure CO2 that you can grab or capture. Brazil had a couple immiscible floods, one immiscible flood. There was a flood in Turkey. It was from an immiscible flood it was from an underground source, and I think the underground source was directly underneath the oil field, so that was convenient. And in Hungary, there were 3 immiscible floods, and those are the ones that the Oil and Gas Journal could track down, at least that I could pick out. So it's not just a U.S. thing, but there's been more activity in the United States than anywhere else. And then I'm going to go into the reservoir technology, and this is the hardest piece of the day. Once we get through this, we can all relax. So CO2 flooding is usually tertiary recovery. It comes after water flooding, and oil fields can be developed in stages, primary, secondary, and tertiary, and usually you go straight through it. I mean, primary production is almost without exception. You start here, you drill the wells may initially flow, or they could be pumped. Sometimes they are pumped from the start. And eventually the reservoir pressure declines to a point where the production rates are uneconomic. And if you're fortunate, there's something else you can do to enhance recovery. And this leads you off to secondary operation. Some of the producing wells are converted to injection. Water or hydrocarbon gas is injected to increase the pressure and move the oil from the injector to producer. This has been going on for a long time. It was going on in the 19th century in Pennsylvania. Illegally, because at one point water flooding was illegal, and they thought it was going to mess things up, but it doesn't. It improves recovery, and then tertiary operations address the oil that secondary recovery leaves behind. In the case of water floods, the injectant is usually changed to CO2. Steam, you might go directly to steam without water, or polymer or surfactants, and it's possible to skip a phase. Usually you do CO2 flooding after CO2 injection after water flooding, but there was a case, I believe it was North Cross, they didn't do a water flood first because the pore throats were so small they couldn't inject water. And Kinder Morgan actually a couple of years ago drilled a new field with a residual oil zone that could not be produced. I mean, it was just residual oil that Mother Nature had water flooded down to residual oil saturation, and they did a CO2 flood from the start. So again, usually you go primary, secondary, tertiary, but not always. So what we're going to be talking about is CO2 and using it as a solvent. And think about this, have you ever tried to rinse oil-based paint off a paintbrush with a garden hose? It just doesn't work very well. You you keep trying to jet off that paint, and it just doesn't all come off. Well, if you use turpentine, the oil just comes off. And propane, natural gas, and CO2 can act like solvents in the reservoir, and they remove oil that was trapped in the pores during the water flood. They're solvents. And they work they work best when they're miscible. And substances are miscible when they're mixed, they form one phase. That is, if you put them together, say in a glass, and you don't see an interface between them, they are one phase. And CO2 acts like a solvent when it becomes miscible with oil. Now, CO2 does not become miscible with oil on first contact. If you were to put them in contact with each other in a pressurized bottle, you'd see that there's an interface. The reason for that is oil is a complex substance with carbon chains of different numbers of carbon atoms. I mean, you work your way up from natural gas to the liquids. You got methane, and then ethane is still a gaseous phase, and propane. Well, propane, we can experience it, well, not directly, but we pick up a propane bottle because they put it under pressure and it's a liquid. And then butane, you actually see it in the old lighters. And when you bring it to atmosphere, it turns into a gas. But substances like propane are going to be immediately miscible with most of the oil. So CO2, when it goes into the reservoir, as it moves through the reservoir, the lighter components of the oil vaporize into the CO2, and that causes the mixture to be more like the oil and more like the heavier components, because now you have some of the lighter components in the CO2 phase, and then the oil sees this CO2 and the lighter components and says, well, I like that better than I like the CO2. And then more of the heavier components come up into the oil. And eventually this CO2 mixture with the light ends of the oil becomes miscible with the rest of the oil. And similarly, CO2 condenses into the oil as it passes, and it makes the oil more like the CO2. So eventually, that's the condensing side of this, and that's how it becomes miscible, not right at the injection well, but some distance out in the reservoir. Okay, so, and I say that, but there's a little bit of a complication in that CO2 needs to be above this pressure called the minimum miscibility pressure. And the MMP varies by oil type and its reservoir temperature. So I got the top plot here, and it shows result of a slim tube test. So what a slim tube is it is a large, it's slim, it's a long tube filled with sand that you can push substances, liquids through. And what you do is you fill it with oil, and then you pump CO2 through it, and you do this several times, usually maybe 4 times at different pressures. And you know how much oil is in the tube because you filled it with that much oil, and you run and you know how much oil is in there, and it fills all the pore space. So the amount of oil in there is the pore volume. You run I believe it's 1.2 pore volumes through there, and you measure how much oil you got. And you can see here in this case, as the pressure increased, the amount of oil that came out as you increase the pressure, the amount of oil that came out increased, and it got to a maximum, and that's where we say that's the miscibility pressure. The bottom plot here just shows, hey, if you look at the density of CO2 and methane and nitrogen, well, methane and nitrogen never liquefy. I'm going to talk about that later. They never really get dense, but CO2 changes phase. Well, it doesn't really change phase. I shouldn't say that. CO2 suddenly gets denser, and the minimum miscibility pressure is going to be approximately equal to the pressure where the density of the CO2 and the density of the oil are the same. So you can make another guess that way, rather than do. do the tests. Now, impurities, they can raise and hurt or lower and help the MMP. You want a low minimum miscibility pressure because if you have a high minimum miscibility pressure, you may not be able to achieve that pressure in the reservoir. And there's a formula which I have not given. It's on a need to know basis only, but it's not hard. But it's not something we need to look at. And there's a formula exists to estimate the effect of impurities on the MMP, and substances with critical temperatures lower than CO2s raise the MMP, and if it's higher, it lowers it. And you've got there, you can see in the middle, carbon dioxide has a critical temperature of 304.2 degrees Kelvin. You got to do it in Kelvin or Rankine to make it work. And if you're higher than that, when you run it through the formula, it hurts the MMP, it raises it. So I did the calculation for us, and a mixture of 90% CO2 and 10% methane has a minimum miscibility pressure of 33% higher than for pure CO2. And if you do an 80-20 mixture, it's 54% higher. And so that's why when you want to do a CO2 flood, you don't want to have these impurities. And this is the hardest part of the day. We get through this and we're smooth sailing. Relative permeabilities. And this is just an overview of this. In general, it's easier for a fluid like oil to flow through a rock if it's the only substance present. If you got some other fluid present like water, it's relatively harder for the oil to move through it, and you have relative permeability curves here I've presented that illustrate this effect. The other thing you'll notice here that there's immobile water and immobile oil exist in the pore space. If they didn't, these curves would go, the endpoints of the curves would go off to 0, 1.0. This is water, it's in water saturation fraction. And so in this example, if you look at the bottom, 31% of the water is immobile because that relative permeability at 0.001 is basically 0. It's immobile. And if you go over the other side to 28% oil, that's 1 minus 0.72. Once you get the water fraction up to 72%, the remaining oil in the reservoir won't move. And then this hysteresis curve that I've got here just to complicate things is only present when you get CO2 injected. And in the case where there's three fluids competing, it gets even harder for each one of the phases to move. And so that's the point there. I mean, the more things you inject, the more phases, the harder it is for everything to move. Second piece here. Okay, let's look at this for another second. In this example, at discovery, the reservoir contains 25% water and 75% oil. So you're at the top left of this relative permeability fraction. I should say here, the total permeability for a fluid equals the rock permeability multiplied by the relative permeability. Okay, so so you're at discovery, and the oil is at maximum mobility relative to the easiest thing to move, and the water is immobile. So you start producing, and you get all oil, no water. And then as oil is produced during primary, the oil, because you're taking oil out, no water, the oil saturation declines and the water saturation increases, and eventually the water becomes mobile. And then you can work your way down, the oil is going from the top left to the bottom right, and the water is going from the bottom left and to the top right. And you work your way through primary. At some point you may water flood, and this thing really accelerates your movement across the curve. As more and more water is injected, the water saturation really increases, the oil saturation decreases, And eventually, at the end of the water flood, the oil is essentially immobile. And that residual oil saturation, the water flood, is 28% in this case. And if you do CO2 floods, you know, there's more curves, it gets more complicated, but the key is at the end of water flooding, the residual oil saturation to water flooding was 28%, and residual oil saturation to CO2 flooding is 2 to 5%. And so you have a big target to get out. Now, you don't sweep the whole thing out because you don't have perfect sweep in the reservoir like you'd have perfect sweep in this little stream tube. But the key here is that the water's, you know, gets hard to move, but relative permeability effects work with CO2 also, because you put the CO2 in, and at some point there's an amount of CO2 that's immobile. So you end up with immobile oil, immobile water, and immobile CO2. And that immobile fraction of the CO2 means that that CO2 is not going to move. And that's useful for the storage part. And we're almost done here with this section. And then I'll ask if we want any questions. There's other processes here, and there's vertical floods, and this could be an immiscible or a miscible process. Okay, we talked about miscibility, whereas one phase, if it's an immiscible process, what it does is you don't get one phase, but the CO2 makes the oil, it swells the oil. If it swells the oil, it takes up more space in the reservoir, and that moves you in a good direction on the relative permeability curves. So this oil gets swelled more, it's more mobile, and it reduces the viscosity, and that's another way to make the oil more mobile. In any case, you inject CO2 at the top of the reservoir. You use gravity to segregate the CO2 in the oil, and you produce the oil down from the bottom of the reservoir. And you may decide to not wait till the oil gets all the way at the bottom, but you could recomplete downward. You have huff and puff. That's an immiscible process. You inject the CO2 into a production well. You wait a few weeks. That's called soaking. And that allows the CO2 to become more mobile than you produce. And then I'm not sure this is a different process, but people call it that. Unconventional. This is injection of CO2 into shale reservoirs. So far, this has been huff and puff. I've heard that somebody's tried to do a regular flood, but I don't know much about that. Seems like it would take a long time. But anyway, I think what people have published has been huff and puff. It at least works technically. The low permeability increases recovery times. I mean, that's what shale is all about. I mean, the overcoming that low permeability is what the production of shale is all about. And I tried to rush through. I shouldn't have rushed through it, but I tried to give us enough time for questions. So I'd like to stop at this point and see if there are any.
And just a quick reminder, this is being recorded, so if you want to go back and look through, you'll be able to do that. And again, there should be a button at the bottom that says raise hand, and I'll be able to call on you to let you know you can speak to ask your question right now. All right, we got one question here. Eric, you should be allowed to talk now.
Thanks. What is the applicability of CO2 flooding to oil wet reservoirs?
Oil wet reservoirs,
Yes.
they work there also. Most of the oil that's produced due to CO2 with CO2 flooding is in mixed wet. But you will be able to get the oil out.
Okay.
Wait.
All right. I think that feedback was coming from Eric. Do we have any more questions? Again, the raise hand is in the bottom, and this all will be recorded.
I'm on my best behavior.
Bay, I have a
Alright.
question. This is Lanny.
Yeah, go ahead.
Yes, I was wanting to ask this question, Chuck. Early on, you talked about your source fields and how we use most of the CO2 out of the source field. Is it possible that we could use those source CO2 fields for CO2 sequestration in the future?
Yeah, that's a good point. I mean, why not put it back? One of your, and we'll get onto this later, when you look at trying to put it in saline reservoirs where you haven't pulled any liquids out, any fluids out, you can't use up as much of the pore space. But there's been a lot of CO2 that has come out of the source fields at McElmo Dome, Sheep Mountain, Bravo Dome, Jackson Dome, and there's no reason you can't put the CO2 back in. I mean, that CO2 was held in the reservoir for millions of years. You know there's a cap. You know it's going to work. I mean, I'm going to say this. I am absolutely certain you can store CO2 in reservoirs and it's not going to come out. I think it's expensive, but I am absolutely certain this is going to work. And you certainly could put those back in those fields.
Sweet. So just to keep us on time, I think there's no other questions right now, so we'll keep going forward, Chuck, and then I will come back on during our break just to let everyone know what's going on.
Okay.
Take it away.
Take it away. All right. Click and on. Oh, look at that. Well, yeah. So anyway, we're on well-designed surface facilities and operations, and we hit the hardest part. Now we're going to take a look at water flood and CO2 flood differences. I mean, water flooding's been around for a long time. And then what do you do? Because most of these fields start with water floods and they move to CO2 floods. What's the difference? Well, CO2 injection operations are at higher surface pressure than water injection operations. And the reason for that is CO2 is less dense than water, so a higher surface pressure is required for the same bottom hole pressure. I mean, you know, if you're trying to inject a gas instead of a liquid, you know, you're going to have a lot higher pressure. And it could require modification to wellheads, but in almost every case it doesn't, because the engineers chose 3,000-pound wellheads, and you just don't need to go that high in most cases to get the CO2 in the ground. A lot of the cases in West Texas, the surface pressure when injecting water is 1,400 psi, and the injection pressure with CO2 is 1,800. So you're well within the limits of what you've already installed. So that's not a, turns out it's a concern, but it turns out to be rarely come into play. Then you've got corrosion, and dry CO2 is absolutely there's no corrosion problem, none. There's the Cortez pipeline, which I was in charge of operating. It's a 500-mile pipeline. Claims to be the largest CO2 pipeline in the world. I don't know. We claimed it. At least if you have enough adjectives on something, I'm the tallest guy in Houston. So we could open up that pipe and you could still see the mill stamps. You know, when we did maintenance, you have to open it up by regulation. You have to look at things every once in a while. So, but the combination of water and CO2 poses severe corrosion problems. And there was I think one of the first attempts of this was in, California. I'm not remembering. The field was onshore. They injected CO2 with water, re-injected what came up, and that ate through the pipes in 2 weeks. So he's like, you know, this is terrible. But there are ways to stop that corrosion. So that doesn't have, that's been solved. You just have to know it's coming. So let's take a look at some CO2 properties. It's quite a compressible fluid. And I have two examples here, one on the left and one on the right, and I'll work through it. And this is for this Cortez pipeline. It's 500 miles long, 502, but 500. And it's 30 inches in diameter. It's big. And if let's just say this CO2 along the whole length is at 70 degrees Fahrenheit. And let's take that pressure from 1800 PSIG to 1900. So what happens, and the Cortez pipeline is filled with CO2, but let's do a thought experiment and say, well, what if it was filled with water? What if it's filled with methane? What would happen? Well, you would add 20 million pounds to inventory in this terms of CO2. If it was water, it was 0.8 million pounds, and methane was 18 million pounds. So in this case, the CO2 is acting more like methane than water. CO2 is squishy, and it is actually, when it's transported, it is in the dense phase. If you, which is, you are above the critical temperature and really beyond the critical pressure. So when you compress this CO2, you never reach a dew point. It goes directly into what's called the dense phase, where CO2 has both the properties of a liquid and a gas. Let's do a little different. Let's increase the temperature of 1800 PSIG CO2. So now it's one pressure the whole way of CO2, methane, or water. And let's just increase the temperature. Well, then in CO2's case, the temperature increases from 1800 PSI to 2300. For water, it's to 2250. And for methane, it's only 1910. So in this case, the CO2 is acting more like water. It also illustrates the fact that you never want to trap CO2 between two valves. I mean, that's you should always have a pressure relief valve, because if if you have a meter skid or something and you turn two valves closed to do some sort of maintenance or something, and you wait for a little bit and the temperature rises, that you really could increase the pressure beyond the point you have designed. So that's one of the interesting things about CO2. And then let's talk about corrosion, because it's the first thing that people are worried about. In fact, at one point in my career, I tried to put in a CO2 pipeline system in the North Sea, and we were going to capture CO2 from a coal plant in Denmark and take it out into the North Sea and take it to the oil fields out there. And the first thing that the people from Statoil, now they're Equinor, they said, "Oh my gosh, we're going to be full of corrosion." And we said, "No problem." And they said, "Well, we're offshore," and I just had to shut up because I've never worked offshore. But for onshore, it's been fixed. One interesting thing is the presence of H2S. H2S, hydrogen sulfide, is normally thought of as a corrosive agent. It's also a rather dangerous gas, but you usually think of it as a corrosive agent. But oddly enough, at certain partial pressures, and these partial pressures often partial pressures that you see when you're operating an oil field, it can create a passivating layer on steel, like aluminum oxide on aluminum, and reduce corrosion from carbonic acid. And there's a picture here of this corroded tubing, and what we're used to is rust, and that's iron oxide, and iron oxide flakes off, but aluminum oxide forms a one molecule layer thick layer that doesn't flake off. And so the oxygen can't keep attacking more and more of the aluminum. That's sort of what happens with H2S. Interestingly, higher carbon content in steel favors adherence to protective corrosion products and corrosion inhibitors. And there's different ways to achieve certain steel specifications on burst strength or ductility and all this other things. And you can get there by adding different amounts of carbon, different amounts of nickel, or different types of quenching, or how you cool down the steel, all these things. But it turns out that the higher carbon content's helpful, and that's not something you usually think about when you're ordering steel. There's a lot of corrosion resistant alloys that you can use. 316 stainless steel, 13 chrome, and Monel. 13 chrome, for example, is the type of casing that is used at the McElmo Dome source field, but they don't even use tubing. They use 13 chrome, and there's been tests to look at how's that work, and there's no corrosion in that casing, and they're tubingless completions. So this type of chrome is very nice, very expensive. There's only a few mills in the world that make it. It's generally made in Japan. There's nickel plating, polyethylene thin film epoxy plating and coating that you can put on various surfaces. You have to, it's not really corrosion mitigation, but you have to specify your elastomers a little bit different. But if you put in the wrong kind of elastomers, they won't hold. Generally, the problem isn't the first time you use it, because the CO2 may get into the elastomer. It might actually make it seal better for a little bit, but if you ever break the connection or something, and then you depressure that elastomer, it can deform. So generally, high durometer elastomers, which means high hardness. When you punch it, it's hard. Those work best. You can inject corrosion inhibitors. You can inject those downhole. You can inject that in conjunction with scale inhibitors. If you inject it down at the bottom of the well, you form a layer, a corrosion inhibition layer. You take that all the way back to the facilities. Cement is you can use that for corrosion mitigation. And so I just want to leave you with, there's lots of ways to solve this problem. The problem is coming, so that's why there's engineers. They said, okay, here comes a problem. This has been solved. I know you call people up and they'll tell you how to solve it. All right. And then, when you put in a CO2 flood production system, a lot of it just stays the same as that you had with the water flood. You have to add a CO2 injection system, a bunch of CO2 injection lines, and an injection skid at the wellhead, the injection well. You have to beef up your gas gathering system, make sure that it's ready for the CO2. A lot of times it's just not big enough. The flow lines aren't big enough. You have to improve or add flow lines. There's be changes to the gas plant system. And this is all a closed loop. I mean, CO2 comes in, oil comes out, and the CO2 is always re-injected. And then the water supply or disposal matches make sure that you can't keep bringing in, make sure everything's in balance. And so let's talk about one of the most obvious things you've got to do with the CO2 is you got to recycle it. You do not vent this stuff. And later on, I'll add up some numbers and show you the stuff's not vented. So you recycle it. You use compressors to recycle the CO2. Pretty standard. This is shop construction of 5,000 horsepower compressor that could compress 30 million cubic feet a day. Once cool CO2, I think CO2 is really a cool substance, but cool CO2, not heated. Once you get above 1500 PSI, it can be pumped. Once you get it above, say, the triple point, which is at, I think, 1154 PSI, it's in the dense phase, but you want to get it a little, you always want a safety measure. So once you get above 1500 PSI, you can pump it. You don't have to put it into a compressor. And that's because it's in the dense phase. It's acting like a liquid. And all the CO2 pipelines use pumps. And interesting, it actually saves energy versus pumping versus using the compressors, the efficiencies, that sort of thing. But it increases the complexity because now you got a different type of piece of equipment. You might have a whole bunch of CO2 compressors going into one pump, and that means if the pump goes down, then your whole system's going down. And so you might prefer having a whole bunch of compressors and not having one weak link. What else goes on? Well, you've got gas handling options. And this is the simplest one. You separate the oil and water out, then you take the CO2 and the gas. And in this case, the gas is 82% CO2, 17%, that's C1 plus, so that's all the hydrocarbons, methane, ethane, propane, whatever's in hydrocarbon gases you've got. And then this would be about 1% nitrogen. And you can take that and compress it and put it right back in the ground. But remember when we talked earlier about those impurities, and you're trying to maintain a minimum miscibility pressure of your injectant. And here you've got 17% methane plus, and you got nitrogen. Nitrogen is bad. Well, you got to check that out. And that's why you have reservoir engineers and people to figure this out. But if you remember, you won't, but if you were to look, you would see that ethane is slightly better for miscibility than CO2, and propane really enhances things, and you might get some butanes in there and so forth. And so you're not just injecting methane, it's methane plus. And when you're getting ethane's no hurt, but propanes and butanes are very helpful. And so when you throw that whole in, the whole mixture maybe work out fine. It's a calculation to make. Or you could go whole hog and really add a lot of gas processing equipment. It adds cost, but you may be able to sell more products. And that's the calculation that you make. It really doesn't add or detract from recycling the CO2 or carbon management, but it's something you can be done if it's profitable. So in this example, same example, coming out of the reservoir at 10 PSI at 375 PSI, running it through a compressor to get it up to 375 PSI. Then you go through dehydration and refrigeration. So you take the water out and you refrigerate it, and now you knock out some NGLs. Why? Well, you like the NGLs because you can sell them, or you can't take that NGL and you can put it back in the reservoir if that's floats your boat. But you're sending them to membranes, and membranes hate fluids. They especially hate water. They are like the wicked witch of the West. They do the same thing. So if you want to be Dorothy, then you can take the dehydrator out and see what happens to your membranes. You will be sad. It will be the end of them. And they don't like a lot of NGLs. They can take some. They really hate water. They prefer not to have the NGLs, but they'll tolerate them. Then you run it through the membranes, and what happens in the membranes is you run it through there, and the CO2 and the and H2S, well, H2S go both ways, but the CO2 comes out in the permeate, unfortunately, at the low pressure, because this is where you're getting most of your gas, and you're going to have to compress it back up. And the high pressure end comes out, and then you might add another stage of NGL recovery or of separations, depends on how much you need to separate, and you put it back in the ground. That's on the bottom. But as you go off to the left, you may already have a gas plant out there, and that may be what's really determining how many stages of membranes you have. Because if you can match the old inlet, you can use your old gas plant. And in this case, it was 8% CO2, 92% C1 plus, and then you have a little nitrogen. And you know, all that CO2 was at this particular plant is probably captured at the plant and sent back to the oil field, because again, you have a need for the CO2. So that's an option. You can go whole hog, or you can put it right back in the ground. So, but there's some additional reservoir considerations. On the reservoir side, on well management, some on facilities, we kind of talked about some of the big ones, and then some safety. A lot of what you have to do on reservoir management is manage the purchase volumes and the recycle volumes. The CO2, you'll see, is the biggest single cost of accessing the CO2 is normally the single biggest cost in your CO2 flood. So you have to manage the volumes, and you've got to manage the recycle, because you have a long-term contract that you've entered into most likely, and you have to be able to buy it on schedule. And then you have to make sure that the recycle volumes do not exceed your plant capacity. And it's all a circle. In these, the CO2 flood kind of, because it's a circular, it's kind of end up being a little bit like a plant, like a gas plant or something. So let's see, what do you do? How do you manage this? Well, when I was selling CO2, I used to throw this plot out, and the more CO2 you put in the ground, the more oil you get out. If your CO2 contacts oil, you will move it. I mean, above the minimum miscibility pressure, you absolutely will produce more oil. It's not hard to make oil with CO2 flooding. It's hard to make money CO2 flooding, but it's not hard to make oil. What we have here is a plot that was done by a man, Mr. Hadlow, who worked for Exxon. He published this paper in 1992, in which he forecast various recoveries at the means field. And these were simulations over time, and then they had an incremental recovery. It was in terms of original oil in place. And this was a WAG. It was a simulation, 2-to-1 WAG. That meant 2 parts of water to 1 part of gas, and gas is CO2. And he made these 4, well, I've extracted these 4 simulations. And what you see is, as you increase the CO2 slug size, and this is sized to hydrocarbon pore volume. And a hydrocarbon pore volume is the amount of original oil that was originally in place in terms of the pore volume in the reservoir. So when we talk about original oil in place, we're talking about stock tank barrels normally, and that's what you sell. But when you put it back in the ground, you have this B sub O factor that takes into account the fact that you're recombining it with the natural gas, go back in the ground, and you're putting it under higher pressure. You got a number there. So the hydrocarbon volume is how much oil was in the reservoir volume when you discovered it. Okay, and if you scale the amount of CO2 that you are injecting, Then you, over this time, you have 0.2, 0.4, 0.6, and 0.8 hydrocarbon pore volumes. And as you put more, as you buy more and you recycle more, you get more oil out. But you'll notice that there's diminishing returns to a factor, because the difference after 50 years between 0.2 hydrocarbon pore volumes and 0.4 is about 4% of the original in place. And the difference between 0.6 and 0.8 is about 3.5% of the original in place. So you're not getting as much oil out for the same incremental amount of CO2 you're putting in, which is not a surprise. This is a rather robust field. I mean, after you've paid for all of the infrastructure and all of your gas processing, you know, there's not that much of a difference between 0.2 and 0.4 and 0.6 and 0.8. So you just keep going. So this is, engineers spend a lot of time looking at this particular type of plot. This is cumulative hydrocarbon pore volumes of CO2 injected versus cumulative incremental oil recovery. So somebody has forecast, say, the water flood recovery, and now you're plotting how much extra oil you got out. And this is often a plot that you use to compare fields. And the vertical, like jagged, that's because there might be a long water cycle. Well, what that means is that this is going to be for an injection pattern, because in the entire field, you're not ever always injecting all water. You can't do that because you have to recycle the CO2. But for an injection pattern, you are injecting either CO2 or water, and you're seeing how the oil production is increasing. It's kind of jagged. It's a little bit harder to work with, but it's fine. It turns out, you know, I look at 0.3 hydrocarbons pore volumes injected and only 3% of a hydrocarbon pore volume produced, 3% original in place. I'm not sure this is a particularly good pattern. In any case, you often have this. If you go to the literature, this is what you'll find. But you'll never know what was happening during the water cycle, and that's just lost. If you have your own field, you may be using this particular flood, and you'll see there's two differences. The first one is we've added the cumulative CO2 produced in terms of hydrocarbon pore volume. And the x-axis is different, because now you've got cumulative CO2 plus water injection in terms of the fraction of hydrocarbon pore volume. Okay. And that's a smooth curve. And so you can easily find where you are on the, on the curve, and you can forecast you can forecast future production because it's not jagged. You have to know what your WAG ratios were over history, but in general, if you go back, CO2 oil recovery is more related to the cumulative, or how much CO2 you put in, than to how you get it out or how you injected it with how much water. So, you know, you spend a lot of time on this trying to nudge it up or then make sure that you don't produce so much gas that you overrun your resources. So we've talked about WAG, and then the question is, well, how do you know how much oil, or how much CO2 to put in versus the water? I mean, is there some formula? And there really isn't. You can simulate it, but your simulations aren't going to be very good until you have history in your field. So what do people do? Well, you start with a continuous CO2 injection. What that does is that bumps up your oil production as fast as you can. Then you WAG, which is injecting water alternately with CO2 to remain within the CO2 supply limit. if you want to just get oil out, you would never inject water. But is more you inject more and more CO2, more and more gas is coming back at you, and you can only handle so much of it. And so you've got to inject the water to tamp it down. And people say wagging may improve the aerial and vertical sweep. I don't know. There's, I think the main reason is you keep it within the facility and CO2 supply limits. There were tests done on these. Oh gosh, what are they? Oh, it was just 2 plates of glass with the beads in between. I cannot remember what the name of those are. Floods that you do in a laboratory, and you could see the CO2 spearing through the reservoir. But and so wagging was supposedly going to help, but before the oil, but there's other simulations that showed that before you get breakthrough, actually the oil bank increases in those areas and pushes the CO2 in other areas. In any case, you got to have water to keep the CO2 production down. What do you do with the wells? Things have changed. On the artificial lift, you've got to decide on a strategy and you got to keep with it. You can gas lift. CO2, when it breaks into the well bore, it's going to act like a gas. It's going to act like gas lift, and you might be able to just have the wells flow again. Some people use the CO2 because it's available as gas lift, and so they actually put the mandrels downhole and do all that stuff. Or you can go to a beam pump or a submersible pump. But if you decide to go to a submersible pump, and you would only do that if you had a lot of fluid, you cannot allow so much gas to break in that you gas lock your pump. And the same sort of thing with beam pumps. Beam pumps are more tolerant of the extra gas. You can have something called flumping, where they're flowing and pumping together. But you want to keep things steady state. And if you have gas lift of some kind, either natural gas, either naturally because you have so much CO2 going through the reservoir, or because you have a gas lift, you dare not put so much water in that you stop that process. So you try to keep things on an even basis. When you do remedial work, things have changed a little bit. The CO2 has lowered the pH. That's the carbonic acid. That's the acid that causes the corrosion. And you've lowered the temperatures. And what's going on with that? Well, when the CO2 breaks into the well bore, it takes a pressure drop. And most of the pressure drop happens right around the well bore. There's the Joule-Thomson effect. It's quite pronounced with CO2. So you really drop the temperature, and you can drop that temperature to near freezing. Freezing for water. And so what does that do? Well, that'll give you, all those things together gives you increased gypsum. So you might need to use some phosphonates inhibitors, and the chemical company will help with that. You get increased paraffin because it suddenly got colder, and you also get increased asphaltene depositions. But these have never really, these are problems they've never, some people talk about asphaltenes like it's going to destroy everything. I've never seen asphaltene deposition stop a CO2 flood. In fact, it's never been, I've seen it happen in one well or another in a field and not another. Don't know why, but so that's what may happen on the remedial side. On the CO2 side, the CO2 breakthrough, how do you fix this? Well, we talked about it. Increase the WAG ratio. That's easy. You can do cement squeezes and plug backs. That's cheap, especially cement plug back. I mean, if your problem is at the bottom of the well, just plug it off, either on the ejector or producer. A little more expensive are these gel polymer squeezes, where you can squeeze them out into the reservoir, and it doesn't go far, but it goes a little ways. It might fill up some fractures that might be there better than cement. They work. A lot of it comes off the market technology that was MARCIT, I think Marathon figured out a long time ago when they had a research lab in Denver. You can use fiberglass liners if you don't think you can do a good cement job. You have selective injection and production equipment, and that's where you have these sliding sleeves. And they've got better and better. I've seen them we used them in our unfortunate adventure into the horizontal San Andreas play in West Texas. No, we didn't use them. Our friends used them. But they've gotten a lot better. And in the Weber sand unit in northwestern Colorado, Chevron has used this production equipment and really improved their recoveries. You can also choke back production and to help divert injected CO2 elsewhere. That works. I mean, just changing how the CO2 runs through is sweeping the reservoir is helpful. You don't usually start there though, because you like to get that oily oil, but choking it back in a few wells and changing up the stream lines could be helpful. Okay, that was a lot on the regular old floods. Now talk about top down. I talked about that a little bit earlier. Here's a nice picture of Wellman, which is in West Texas. It's more of a pinnacle reef. They do this a few places in Texas. I believe that's what they're doing up in Michigan, where they're taking anthropogenic CO2 and putting them in these reefs. The problem up in Michigan is there's not as much CO2, not as many sources as the oil folks might like, at least ones that are close to their fields. In any case, you produce from the bottom, you generally recomplete downward. You can use logging observation wells or material balance, and you can follow the oil water or the gas oil contact on the way down. And there seems to be like a 50 feet of a messy interface of it, and you just recomplete downward. And these work. Metering, just saying, usually custody transfer is done with orifice meters. I have heard of them using the wedge and Coriolis meters also, but usually it's orifice meters. They're accurate to within 1% or less. I mean, and they're just simple, very, very simple meters that are used every day in natural gas. And the important factors are differential pressure, same as natural gas, molecular weight and density. And the molecular weight and density are, well, they're key, but they're in the formulas they're used. They're also key because if the CO2 content is changing, if it's not 100% CO2, you want to make sure that you know if the density is changing, then you got to know that. And that indicates that the content is changing. For the underground sources, it's underground, they rarely change. And non-custody transfer ports, they use turbine wedge and Coriolis meters, and generally at the wellheads, at the injection wellheads, they use the turbine meters to allocate injection into the field, into the individual well. And then there might be orifice meters, certainly at the custody transfer point, because that's where your money is being exchanged. But there also could be an orifice meter as you come out of your plant, so you know how much recycle you're using. And then you use the turbine meters to allocate amongst the wells. And safety, it adds several complications. I mean, the most obvious one is asphyxiation. CO2 is not oxygen. Asphyxiation can occur whenever the concentration in air drops below 16%. Normally it's 21%. and most people can tolerate, most with normal cardiovascular and pulmonary respiratory neurological functions can tolerate exposure up to 0.5 to 1.5% CO2 for several hours without harm. The current US standard for a maximum allowed CO2 concentration is 0.5% for 8 continuous hours or 3% for a short time. I really don't, I mean, the way this, I mean, if there was a release, I don't think you would asphyxiate. I think you would just run away. But the problem would be is what comes with the CO2, because there may be H2S with it, and that would be what would get you. I don't think there's anybody that's died from CO2 asphyxiation. CO2 is heavier in air, and it can pool under, you know, in low spots. It could pool in cellars around wellbores, so you need to be aware of that and careful with that. But I don't think there's been a release where CO2 has killed anybody except when there's been H2S, and the H2S is the issue that you have. Another source of danger is the high pressures, because you generally transport a lot of the CO2 in the dense phase, which is above, you know, 1200 psi, usually above 1500 psi. So suddenly now you have a lot of vessels that are in the field that are at higher pressures. That's a standard thing that's people are, you know, used to dealing with in an oil field. But, you know, you have more of it than you did at the water flood. The last two are not as, I mean, they're again possible. You've got, you got noise levels. If you were to vent CO2 during a maintenance, some sort of a maintenance event, it can get quite loud. But that's why we have hearing protection. It's simply, you need to know. If you know that, you're ready. The last one, frostbite. You know, this is, CO2 can form when it takes a big pressure drop. You can form dry ice. So, you know, if you see a bunch of dry ice, I mean, don't lick it. I mean, I don't think, no one is, I should say, no one's dumb enough to really have a problem with this one, but it is a potential. And that is, oh, we're at the 10-minute break.
Yeah, perfect timing. So we went a little bit over time, so we will hold questions for now unless anyone has anything quick. You can raise your hand. I'll wait a few seconds if you got a question to look for raised hands. But we will try and get back on track. We have a question coming up. I'll get to you quick, Dylan, but just for anyone that needs to take a quick break, we'll try maybe come back at 11:31, 32. We'll give you a little bit of time to come back just to keep on track though. So let's see, Dylan, you should be able to talk now.
Yeah, my question, can you hear me?
Yes.
Yes.
Okay, my question is, what is the typical residual oil saturation to gas injection, or let's say to CO2 injection, based on your experience?
Well, the typical CO2 residual saturation, okay, there's two things. One, what is it in an experiment? In an experiment, it's 2 to 5%. But if you were to run this, say, through the CO2 profit model, which is a nice DOE program that still works. It still works, yeah. But you can't stick in that 2 to 5% because that's not taking into account the sweep efficiency of the reservoir. So I usually put in 10 to 15 to make it come out right. Because, you know, but if you were, I mean, that's the difference. I mean, if you could simulate everything perfectly, it'd be 2 to 5%. And the more, but you have to take into account the fact that your sweep efficiency isn't perfect. Does that help? Did I answer the question?
Yeah, it's okay. I know normally, when we're running these simulations, you typically put like 5% as the residual saturation. And now we don't do a lot of experiments, to be able to get this number. So yeah, it's very helpful. Thanks.
The 5% is a good number. It's a good number. And if you simulate enough of the reservoir to take into account the sweep efficiency, then that 5% is a good number.
Well, thank you, Dylan, for the question. We will take about 3 or 4 minutes now, just a quick break. We will have a really long break coming up at 12:10 Central Time. So whatever your local time that is, for a quick lunch break for about 30 minutes.
3
Feel free to
minutes.
step away.
No,
Yeah,
Bay, why don't
and
we,
it's really-
why don't we come back at 11:35 or so, give people, and Chuck as well, a few minutes.
Sounds good. Perfect. We'll see you all soon.
Oh my gosh. Okay, so.
Chuck, we'll start in just about a minute or so.
Okay.
Chuck, you're doing a great job.
Thank you.
Chuck, if you want, it's 11:35. If you want to
I'm
get
ready to go.
started. Okay.
Yep. Okay, back at it. Regulations. I am, this is with trepidation that I enter this, this subject. So I know many people here know much more than I do. I'm hoping that some of you know, no less. So this is worthwhile. All right, so I'm going to spend a lot of the time here comparing the class 2 wells and the class 6 wells. The class 2 wells are the ones we know and love. I don't know if we love them, but they've been around for a long time. And they are associated, they're wells that inject fluids associated with oil and gas production. All right. And they are primarily brines, which salt water, that are brought to the surface while producing oil and gas. And they could be other trace things like methane or something that didn't get pulled out, but it's generally brines. And the categories are disposal wells, enhanced recovery wells, hydrocarbon storage wells, and the enhanced recovery wells, the ones we're talking about. And they have fluids consisting of brine, fresh water, steam, polymers, carbon dioxide, are injected in oil-bearing formations to recover residual oil. And in limited applications, you can inject natural gas too. Natural gas can be used. Those have been around for decades. And then in order to address geologic sequestration, the class 6 wells were created. And that's where you inject CO2 into deep rock formations. I'm just reading it for purposes of long-term underground storage or geologic sequestration. So these are purpose-built wells for geologic sequestration. So let's take a look at the class 2 wells that many people are more familiar with. And this is really about protecting drinking water. And it lays out requirements for construction, operations, monitoring, testing, reporting, financial responsibility and closure. None of this is particularly difficult. Well, I'm sure it was difficult at the beginning, but everybody got to know, hey, this is what you do. In general, okay, you got to show that the injection formation is competent to contain the injected fluids. That's, if you're going to put it in, it's almost a given, but got to look at it. This is where you get in trouble. Nearby wells that penetrate the formation don't provide a pathway for the injectant to migrate, get up to the potential drinking water reservoirs. And if you encounter, these would be generally old poorly plugged wells that were plugged before there were regulations. And if you find those, you got to fix them. It's not always easy. You have to show the injection process does not cause the injectant to migrate. And this is really that the injection pressure and injectant, well, you're not going to inject above frac pressure. That's pretty much what they're talking about there. And the injection well itself during its life and after abandonment doesn't provide a conduit. So it's a lot of the same criteria that you applied to nearby wells. Well, you got to make sure this one's set up too. And you can fix it a lot of times by perforating and circulating more cement behind pipe at the appropriate places. So a lot of times this stuff can be fixed. It's not exhaustive, but it's pretty close. Well, class 6, it has an additional concern, and that's assuring long-term storage of CO2. And then CO2 introduces some unique, has some unique characteristics, and you need to look at the relative buoyancy, the subsurface mobility over a long time. That's key. The corrosivity in the presence of water. Talked a little bit about that, but not related to the class 6. And the large anticipated injection volumes. Okay. And a lot of the overarching requirements are really the same. I mean, if you love siting, construction, operation, all this, I think siting is a different one, but that's where you really get hit. I mean, it's an extensive site characterization requirement. And we're going to go into detail on all this, but that's the big change. Then you've got to have construction. The materials have to withstand contact with CO2 over the life of the project. There's operations. You've got this comprehensive monitoring requirements and well integrity, the CO2, injection and storage, and it goes into post-injection site care. So there's a lot of monitoring. I mean, then you've got reporting. Okay, you got to tell people. It tells you how to tell people you're doing the right thing. A closure, it's not that big a deal. Well, it shouldn't be if you've done everything right up to this point. And in financial responsibility, I admit I don't know. I've read the regulations, and I think we're just still feeling our way forward on that. Okay, what are you doing with the siting? Wow. You know, there's a difference here with the class 6, because if you have the class 2, and you can use class 2 to store the CO2, but you know a lot about the area because you've drilled it, you've drilled a bunch of wells, you know, it's been an economic incentive to understand what's there, and you know that the reservoir or that the seal held the oil for millions and millions of years. So you've got a lot of the questions are already answered, but when you go to a class 6 site, you're almost at ground zero. So you got to look at the regional geology and hydrogeology, the structural geology. You got to look at the faults. Faults are a big deal. Seismic history, geophysics. You got to look and here the confining and injection zones, because you don't even worry about the confining zone when an oil field, because it confined it. I mean, you didn't worry about that when you were looking for oil. Well, in the exploration, but when you're production, you know, it's just there. Here, you got to look at the thickness, the facies, mineralogy, all these different cap pressure, geochemistry. And then for the injection well, you've got all these different things you've got to do with the logs and formation testing and taking cores, bringing it to the surface. You've got injectivity and fall-off testing, fracture testing. You got to characterize the injectant and check the compatibility with the injectant. And the injectant might not be 100% CO2, but I doubt that the other elements, compounds are in there are going to be a problem, but you have to look at it. And then you've got to look at the existing wells in the area of review, which it's just a circular process because how big is the area of review? Well, you got to characterize the area to know. So, and then you got to, and once you know what the area of review is, you have to go back and characterize it. Anyway, it's the region surrounding the project where U.S. drinking waters may be endangered, okay? And then this is a big deal, defined by compositional modeling. This is, I mean, this whole thing is a consultant's dream. And then you've got to project the lateral and vertical migration of the CO2 plume until it ceases to move. Okay. Pressure differentials are so low that CO2 can't move into a U.S. drinking water or the end of a fixed time determined by the UIC program director. And I guess in a lot of cases, they're just going to have to say, good enough. You know, what is movement? Is it one inch in 30 years or 100 years? I don't know. But you got to simulate hundreds of thousands of years. You got to calibrate the model every 5 years. This is the consultant's dream. And then you could lead to corrective action on existing wells. So this is a project, literally, given the length of time, if you get this, you can give this to your grandchildren. There's some construction. I'm going to focus on the differences between class 2 and class 6. The casing, you need to select corrosion resistant material for the life of the project. And that's going to lead to choosing materials like 13 chrome for the bottom of the well. So maybe not the whole way down, but where you expect to have the CO2 in contact with it. And then you have to cement every string to the surface. That's not true with class 2 wells. And the tubing's got to be CO2 resistant. And I put in that at least inside. I don't think this, depending on what you're injecting with the CO2, the tubing, bare carbon steel may be good enough because dry CO2 is one of the easiest things to deal with, not corrosive at all. But there, you may be bringing H2S in with it, and that might not be at the right pressure where this all works out. So you need, that's something to worry about. Not be worried about, to investigate. Then the monitoring and testing. This is really some things to do. Your mechanical integrity testing, you got to do that anyway with your class 2 wells, but class 6, you've got to, you do a pressure test internal with the tubing and packer. And interestingly enough, during operation, usually the annulus pressure needs to be greater than the tubing pressure. So that means if there's a leak, it's going to leak into the tubing and then down into the reservoir and not have the CO2 leak into the annulus and create carbonic acid and cause a problem in the casing. Then this is something additional, this external testing. You're looking for flow in channels adjacent to the wellbore. You've got this oxygen activation logs, which I've never used, but you've got temperature and noise logs. Noise, you just listen. Temperature, when CO2 takes a pressure drop, it gets cold, and you should be able to see that CO2 moving. That's new. You've got operational testing, CO2 stream composition, that should be not too hard. Injection rate, volume, and pressure, not too hard. Corrosion monitoring, you got to set up places to insert corrosion coupons. That's not too hard. And then you have to do casing inspection logs. That means you got to pull everything out of the well and then do a casing inspection log and then put it all back together and hopefully it doesn't leak. And you got to do a pressure fall off every 5 years. Not too hard, but stuff you got to manage and do. Then you've got to monitor on this groundwater quality geochemistry, monitor the wells in the first permeable formation above the confining zone. So you're not just working in the reservoir, you're going up hole to find some area that's permeable, not the cap, but the next permeable level. And you're gonna have to put monitoring wells in there and check things out. And you've got to monitor the plume and pressure front. And you're really gonna do time-lapse seismic surveys. I said you can do other stuff, but that's the one that today would work. And then you've got pressure monitoring wells in the injection zone, more monitoring wells. And then maybe you do the soil air and soil gas. That's where you would stick sensors, in the grass in the area and see if there's any CO2 leakage. You don't have to do that. I don't know if you're gonna do it or not. We'll talk a little bit more about that later. Closure, okay, normal plugging, a final external mechanical integrity test, normal plugs, considering cements resistant to carbonic acid. There's a lot that are available. This is not really exotic stuff. There's, you pick class H, class G, put in the right stuff and you're ready to go. Maybe you don't put class C in, but nobody puts class C in. Never seen it. Post-injection care, you got a plan for 50 years of monitoring. And then site closure, you have to jump through some hoops. And then you've got to plug the monitoring wells. And here's the financial responsibility. And this is new. I think we're still working through it. And all this information came from the EPA website. It looks like they've come up with a trust fund is best. They have different ways of doing it, and they have different aspects and phases in the whole process. And trust funds are best, looks like, for corrective action and phased corrective actions and plugging the wells and post-injection site care. And then maybe emergency response is best for insurance. And what would you do? Well, if CO2 is leaking, you can pump water in it and you could trap it in the reservoir and push it out of the way. I don't know, there's just different things you could do, relief wells, whatever. Okay, so you can transition class 2 wells to class 6, but geologic storage of CO2 can continue to be permitted under class 2 program. So that was a big concern that, wait a minute, are we going in an oil field, are we going to redo all the class 6 wells or class 2 wells and class 6? And the answer was no, you don't have to, because you should be monitoring everything. You've got a lot of wells there. And so the use of anthropogenic CO2, enhanced recovery operations, you don't need a class 6 permit. That was good. And you don't have to have the class 6 site closure requirements, because some of the ideas is there's enough of a seal, there's enough of a history. But it does say, if your EOR operations, they're focused on oil and gas, don't have to be managed under class 2, but you could over time slide out of oil and gas operations and into sequestering. And if oil recovery is no longer a significant aspect, what does that mean? I think you know it when you see it. It's one of those things. But there's a big and if class 2 can't manage the increased risk to the U.S. drinking waters, remember class 2 has been handling it all this time, then it should be transferred to a class 6. So that's a little gray area there. Okay, so I'm going to go into carbon balance here. And this was from a presentation and I made this at a Society of Petroleum Engineering meeting in 2008. So some of this stuff's old. Some people have used this information and are advancing it. This is what I got. And this is really to say, okay, does this make any sense? I mean, should we just be putting CO2 into saline reservoirs? Does this make any sense at all? I think the answer is yes. We did our best shot in 2007. Okay, So what we're trying to do is look at the carbon balance of the Sac Rock oil field. Calculation the emissions in 2007, using the California registry methods. It's mostly, but where we didn't, we were more punitive. We're going to compare various emission sources, and I'm going to comment. I'm going to show you how some of the calculations, how they get made. We're looking at it at Sac Rock. We talked about that earlier. It was the first major CO2 flood done in the world. There were a few earlier ones, but this was the first big one that lasted. It is in West Texas, and it's a big field. At one point, it produced more than 200,000 barrels a day. It was founded in the late 1940s. Oddly enough, Bob Hope and Bing Crosby were working interest owners at Sac Rock. So now that's maybe the most interesting thing I'll tell you all day. And they used to fly out in their planes to some working interest owners meetings to take a look at their oil field. Very small owners, but whatever. The end of the allowable, there's a big ramp up in oil production, and it was the end of allowables, and it was the start of the CO2 flood, and that made things hard to figure out what's what. We have made attempts, and you see another bump out in the 2000s, that was a redevelopment because there was not enough CO2 was put in the ground the first time. So here's some numbers, and that's fairly big for a U.S. oil field. Not big if you're in Saudi Arabia, but it was 28,000 barrels a day, over 100,000 barrels of water a day, 75 million cubic feet a day of hydrocarbon gas, and then there was that year 637 million cubic feet a day was produced, and you have similar numbers were injected. 835 wells, and then lots of compressors. It handled, the area handled third-party gas, and there was a Snyder gas plant. So a lot of stuff there. And then the emissions was about 1 million tons of CO2 equivalent because everything is turned into CO2 equivalents. And it was primarily due to energy use, and it was metered. The calculations were based on meter volumes. There were some estimated factors, but there were mostly metered volumes. And we used the California registry methodology totally except for indirect emissions because we thought California was less carbon intense than Texas. So let me just kind of go through these. There was a 103 megawatt combined cycle power plant, and had a lot of equipment. It burned almost 20 million cubic feet a day of gas, 20,000 MMBTU, and we calculated almost 400,000 tons, and these are all metric tons, were emitted from that in 2007, and that should be a good number because you know what went in, what went out, what kind of plant it was. And then there were a lot of purchases. The field used a lot of electricity. It purchased 107 megawatts. Half of it was water, half of it was gas, from gas. And that was 410,000 tons in 2007. But we used the natural gas plant numbers, we just scaled to that because California's numbers were low, would have been lower. So we used, we figured that the marginal plant at that time in Texas was gas. And then we pulled out third-party gas processing from our numbers because we want to focus on the oil field and not clutter things up. I'm just going to flip through. We're reciprocating engines, 89,000 tons. They're starting to get lower, you know. There were flares, and there's 61,000 tons. There were heaters and boilers at 54,000 tons. Vented emissions, these are only if there's a maintenance event. 35,000 tons. Fugitive emissions, 1,200 tons. I thought there'd be a lot more, but there weren't. And I think it's because there were vapor recovery units on all of the equipment. So you didn't have a lot of fugitive emissions. And when you looked at the plants, they are all where you think you get a lot of them. They were, I mean, quarterly, we had people coming out and looking for leaks and doing testing. It's all part of process safety management. And so, there weren't that many. I was surprised. Even went down to mobile emissions on gasoline and diesel, down to lawnmowers. So this was as good as could be done. And then if you say you have a stationary flare, well, somebody says, well, what's in it? Well, you got CO2, nitrous oxide, and methane. You have so much hydrocarbon gas burns and so many emission factors, and you calculate this all out. It is numbers intensive. And so throw it in, well, where does it all come from? Well, it was the power plant. It was buying electricity or making electricity. And that was 39 plus 38 is 77%. And then you had reciprocating engines. And then you had it really was burning things that made a difference. So then the question though comes, hey, how do you know you're putting the CO2 in the ground? How do you know if it's not just coming out somewhere and just leaking to the surface, and this whole thing just isn't going to work? Well, a woman, Rebecca Smith, from the University of Texas Bureau of Economic Geology, came out, and it was with some trepidation when I heard this, that, oh my gosh, no good can come from this. But well, we helped her, and any way we could. She didn't need much help. She had her own research procedures, but we helped where we could. And she performed groundwater studies and measured the CO2 content in the air around Sac Rock. So she didn't find any CO2 or the products of CO2 leakage in the groundwater. She did these she sampled the air right in the grass and a little bit above, and she so sensitive you could even see the seasons. When things grow, CO2 content goes down. When it decomposes, it goes up. She could even see that, and she could not find any leakage at all. I don't know, that may not be enough for you, but if somebody looks really hard for something, they got all these scientific instruments, and they can't find it, maybe it's not there. Sort of like a UFO. Then there's this whole thing I want to get in on retention. Sometimes when reservoir engineers talk about retention, they're not talking at all about whether CO2 is in the ground or it's in the air. What they're doing is it's the amount of CO2 remaining in the reservoir at any given time, which equals the amount of CO2 injected less the amount of CO2 produced. Remember, everything is recycled. And so retention is net utilization divided by gross utilization, which net utilization is how much CO2 do you buy per barrel of oil that you produce, and gross utilization is how much CO2 do you inject, recycled plus purchased, per barrel of oil that you produced? And this gets into how efficient is the reservoir. I mean, how much injected versus produced do you have? But this concept gets out and says, well, we retained half the CO2, does not mean half of what in the air. It means half of what was reinjected. Okay. So what was the carbon balance? In 2007, purchased 4 million tons. And when I say purchased, you have to remember, a lot of this was underground CO2. So this isn't anthropogenic. This is just a calculation you could use later. 4 million tons were produced. The direct and indirect emissions were about 1 million. So sequestered was about 3 million. And the oil production was 10 million. So CO2 equivalents emitted per barrel is 0.1 tons per barrel. So that's a number to come up with. And then looked at, well, what over the life of the field, how's this going to work? And then the thought that the EOR production was going to be 185 million barrels of oil at that time. So the indirect and direct emissions based on 0.1 per barrel is 18.5. There was an effort made to do capital emissions, which are difficult, but how much money, how much CO2 is emitted, building everything, getting it there, installing it. And basically what I was told at the time, Chuck, that's really almost impossible. What you need to do is just take the overall emissions for the country, divide by GDP, and use that for how much money you spent. That's what I did. So about 92% of the CO2 that came into the, if it were all anthropogenic, would be net stored because there was a bunch of emissions through the whole process. And that would be enough for many people, but then there's a question for some of additionality. And that's the thing. What if you don't assume that this oil that we produce here replaces oil that would be produced somewhere else? And what if this is oil that would never have been produced by society at all? And it's can't quite be that true. Neither can be true that it's not, that there's no additionality or it's all additionality. But anyway, the EPA said, hey, there's about 0.3 tons of CO2 equivalents emitted per barrel of oil produced because you're going to send it to, it's going to be burned in the cars and everything else. So throw the additionality in, turns into a big number, but the total sequestered is still 124. So if you throw in the additionality, you're sequestering 48%. So if someone does an economic analysis and the marginal cost of oil or marginal production of oil, then it's going to be between those two numbers. And I believe my conclusion is greenhouse gas emissions are tied almost exclusively to energy consumption. That's where you can go. It's electrical power, gas-fired reciprocating engines, and heat. Greenhouse gas emission calculations are tedious, but there are such people that want to make those, and EOR can sequester CO2. And I think we're at the lunch break, and I'm a little behind, but.
Perfect. No, you're right on time. We even have a couple minutes for a few questions. Again, for attendees, there should be a button that says raise hand at the middle bottom of your screen if you want to ask a question right now. For those who want to step away, we will be resuming at 12:40 Central Time. So we do have a couple minutes if you have any questions. Let's see, it looks like we got a question. Ramon, you should be able to speak. We're not hearing you. If you can still hear us, Ramon, you might need to make sure your microphone is turned on for your computer. We'll give you a second. well, we'll see if we can get Ramon later on. If there's any other questions, we do have a minute left before we're planning to get off for lunch.
Bay, I have a question. This is Lanny again.
Yeah, go ahead, Lanny.
Yes, Chuck, and this is more on your completions of the wells and all that. Does the normal cement handle the class 2, or do we, when we inject, when we just drill our wells and complete them, or do we have to put a special cement into it?
Well, that's interesting. There's been some tests done on the cement that's been from some old wells, and the class 2 cement does work. It was sort of like a self-healing thing, in that the CO2 would go in, but then it changes the cement a little bit, but then that change helps it not go as far. There are better cements that you can use. If you know that you're going to now use it for CO2 sequestration, but the wells that have the old wells, which class H and class G have been injected since the 50s, maybe not class C. They work, and there's Princeton got a hold of some samples of cement from Sac Rock. They came out to look for those, and somebody brought it out from a cardboard box by their desk, and this professor from Princeton, you thought that he'd found the Declaration of Independence in somebody's attic, or some sort of thing. I was like, how could this be? Is searching for the Holy Grail, and it's in some cardboard box and under somebody's desk. Anyway, they took those after we figured out what they were going to do with them, and it worked out. I mean, the cement is pretty good, but there's better cements if you know that you're going to want it for 100 years or so.
Awesome. Well, thank you for the question, Lanny, and for answering, Chuck. Like I said, attendees and panelists, you guys can just step away from your computers, or you can log on. Log off. You just have to use the same exact link you used to join. But I recommend just staying on and coming back to join us at 12:40 Central Time.
Hello.
Hey, Ramon.
Hey, yeah, too late for now? Probably come back later.
A quick question if you want, Chuck, if you have time, really quick.
Yeah. Oh, right. Thank you. Thank you so much. I'm Ramon Gill from the Bureau of Economic Geology from the Gulf Coast Carbon Center. I worked with Vanessa Nunez. For sure, folks know about us. And we were using your study for our study about the life cycle analysis and ERRT life cycle analysis. And the very important finding that we had, and you have to consider it, is that your 2007 carbon balance for the Sacro field, it's a picture in time, but it was very important to know that the CO2 utilization rates vary significant during the time. So we find that during the first initial periods of the operations, you have a net carbon negative emissions, meaning that you're sequestering much more in the whole life cycle analysis than you're storing more than what is emitting. So at the end, probably you can end with a negative balance, but in the middle or in some point, you can transit from from negative emissions to positive emissions. So that's a great point for the manage of the flow, and also the economics of the EOR operations. I mean, it's you can handle that in time.
Great, thank you.
Thank you, Ramon. Okay, so yeah, we will come back at 12:40, maybe a little after 12:40 Central Time to kick things back off. Thank you.
Chuck, you can mute yourself and turn off your video for the 30 minutes.
Yeah, I am trying. Mute. Doesn't seem to want to do it. Huh. Oh,
I
oh,
can mute you. I can mute you.
okay.
Chuck, I can turn off your video as well. What just happened? You guys were perfect timing. I'm right now got 30 minutes for lunch and you walked through the door.
So for everyone joining us, we'll wait a couple minutes since we went over a little bit longer there. But we will be starting back up here pretty soon. We'll give it a couple of minutes. And thank you all for coming back after lunch. Well, Chuck, if you want to take it away,
All right,
I'll
take
let
it
you have
away.
it. Yeah.
Thank you. Okay. So on to screening and economics, we've gone through a lot of the technology. Now we're going to spend, I think, most of the rest of the day on economics and how you make this happen. The first considerations, and this is on the screening, is how far are you from a CO2 pipeline or source? That's probably the most important thing, because you get too far away, you just can't afford to transport it. Miscibility, that's one we've already talked about. Heterogeneity and loss zones. If your formation is very heterogeneous, you may not get good sweep and may be difficult to do. And last is on lease considerations. If you don't have a unit already put together, if it's broken up into too many pieces, you may not be able to do the CO2 flood. So here's some screening criteria for miscible CO2 flooding. You needed the API oil gravity to be greater than 25 degrees in general. For miscible flooding, you need it to be lighter. Viscosity, less than 10 degrees centipoise. 1 centipoise is the viscosity of water. Deep enough for more than 3,000 feet in order that the CO2 can be injected below frac pressure. The temperature, the higher the temperature, the higher the minimum miscibility pressure will be. And we have to have enough residual oil there to make it worth doing. And in general, a good water flood makes a good CO2 flood, and a bad water flood in general makes a bad CO2 flood. And then here's some screening for immiscible CO2 flooding. Your oil gravity can be lower, the viscosity can be higher. There's really no consideration of depth, although you do have to be able to inject the CO2. Similar temperatures, and you've got to have enough residual oil to make it all worth trying. So here's some rules of thumb. They come from West Texas. And this really is just allows you to get into the ballpark when you're thinking about something. You will not be off by an order of magnitude if you use these numbers. CO2 floods normally, they produce 8 to 16% of the residual oil in place. During an initial CO2 slug, maybe 30 to 50% of the hydrocarbon pore volume. And then, like we said earlier, if things go well, you just keep going. And so you could just sort of say, okay, maybe I'm going to get 10% of the oil in place. Okay. First cut. In the Permian Basin, floods often purchase 5 to 6 MCF per barrel of oil produced and recycle an equivalent amount. And this works out to 50, 60% of hydrocarbon pore volume. If you go farther and farther and farther, then numbers may be off. But by that time, you've got a CO2 flood up and going, and you're not using rules of thumb anymore. So let's take an example field of 100 million barrels. Let's say we'll get 10% recovery. That's 10%, 10 million barrels of oil. So if you need 5.5, you need to buy or acquire 5.5 MCFs per barrel. And CO2 in the US is measured in, it's really MSCF, 1,000 standard cubic feet. And if it's a standard cubic foot, it's actually a mass. But it's it's MCF or MSCF. So you need 55 billion cubic feet, and then you probably need 55 billion cubic feet recycled. So you're going to inject 110 billion cubic feet of CO2. And if you want to go back to tons, you can write this down. There's about 19 MSCF, 19 MCF per metric ton. So, so you can make that a little bit more like 19.1, but use 19, you'll be close. And then, okay, you know how much you're going to get out of the ground, but how fast? So first pass CO2 injection converted into reservoir barrels equals water flood injection. And at most of the MCFs that we, in most of the reservoirs that we use or we're aware of, it's about 2 MCFs is about equal to 1 barrel of water in the reservoir. And then notice that WAG, if you inject water, that may reduce water injection by 50% for part of the water injection cycle, because you had a lot of CO2 in the ground, and now you're trying to push water through it, and the water didn't want to go in for a while. And so at the beginning of a WAG cycle, your injection rate could be half of what it might have been before. But over time, it generally, as you put more and more water in the cycle, you go in a little bit faster. Okay, so the project life can be estimated since we know the amount of CO2 to be injected, and we assume that 1/2 the time the water is injected. Okay, and experience shows that the maximum rate of oil production is 1/10. This is for St. Andrews Reservoir, 1/10 of the reservoir injection rate, which is generally equal to water flood injection rate. So you have all these rules of thumb. So let's keep going with this example. Let's say there's 25 injectors each. This is each injecting 1,000 barrels of water a day. So the injection rate is 25,000 barrels of water a day. And if there's 2 MCF per barrel of oil, then you're injecting 50 million cubic feet a day. And over the project life, you're going to inject 110 BCF of CO2, so that's 6 years. But we don't put CO2 in all at once, we WAG it. So it's 12 years if you inject water half of the time. And then if water injects at half the rate of the CO2 injection, the project life is 15 years. All right, so, and let's say the maximum oil rate, if we had 25,000 barrels of water a day and the maximum oil rate's 1/10 of that, that's 2,500 barrels of oil a day maximum rate. So then the question is producing 10 million barrels over 10 to, or 12 to 15 years at a maximum rate of 2,500 barrels a day interesting? I mean, then now, if that interests you, you can do a lot more calculations. So that's one way that you can use rules of thumb to get in the ballpark and for how fast you're going to inject and all the rest of that. Now I'm going to look at a little bit more detailed economics. For a large field in the Permian Basin. And this one is large enough that it benefits from economies of scale. And this is something that Windy Cove Energy did a few years ago when we were looking for CO2 floods. It's in the Permian Basin. And we did the analysis. So I delayed the start date 5 years and repriced the oil and CO2. And it was a big project. It was 900 million barrels original place. That's a big field. There had been 210 million barrels of cumulative production. And then we calculated that the overall CO2 recovery efficiency was 4.8%. There's a lot of field that we found that we didn't think would be thick enough to do CO2 flooding. So the pattern CO2 recovery efficiency was 12.3%. So that's in the 8 to 16% And the gross utilization rate was 13.4 and the net was 6.7. So the net utilization is how much you would have to buy. The gross is you're recycling. And the CO2 storage was 290 billion cubic feet, was 15 million tons. So that would be the size of this project. Let's just roll through this table. And these are the CO2 flood economics at $50 a barrel. And the revenues were going to be $1.7 billion. Operating costs almost 600 million. You had production taxes. G&A, that's overhead, was 152 million. And then you had the CO2 purchases. And I put it in $1.50 an MCF. So that's, multiply that by 19. And what would that be? I had that in my head. 19 times $1.50, that was $28.50 a ton. You see that CO2 purchases are one of the biggest pieces. There's a CapEx, and then that cash flow at the end of time at $50 a barrel is $79 million. And you're not investing all that time and effort to get $79 million. And indeed, you look at the discounted cash flows on the far right, it's negative 77. I mean, this doesn't gonna work. And when we were looking at this, the oil price was $65 a barrel, so it wasn't dumb. You're not gonna do this project. The internal rate of return is 4%. The payouts, 11 and a half years. If you exclude G&A, it's 9.5 years, and that's usually within a company, you exclude overhead because you don't know what it is. But if you're starting a company, you know how many people are going to hire. And the CO2 price as a percent of oil price is 3%. So what that is say oil price is, well, oil price was $50, CO2 price was $1.50 an MCF. So that is 3%. So it's oil in dollars per barrel and CO2 in dollars per MCF. $100 a barrel, 2%, $100 a barrel is $2 an MCF. So that's that calculation. If the oil was 60, right, the IRR goes up to 16%, 22% excluding G&A. The payouts without excluding G&A is 6.5 years. And CO2 price as a percent of oil price is 2.5. You're on the edge of getting this one over the line. A lot of companies could not possibly wait 6.5 years for payout, but if you're in a bigger company or you have patient capital, they might do it. One of the issues you have is that CO2 price as a percent of oil price is 2.5%. What I've noticed is if you don't get it down to 2%, you're going to struggle. And early on, the floods that came in had a little bit higher price in terms of oil, but they were much bigger and they had more economies of scale, even bigger than this one. So, $50 CO2 flooding is tough. And let's look at, how you can, what's it sensitive to? What's the internal rate of return sensitive to? Well, number one is oil price. Oil price is always king. If you just knew that, you'd know what to do. But after that, CO2 turns out it's the next biggest parameter, cost parameter. I mean, operating costs slightly larger, but there's a lot of pieces to the operating cost. CO2 is the single biggest piece, and capital is large too, and G&A. And this is an effect on a 10% change in factor. So if your so this is how much it would go up or down from that 4% in the $50 a barrel. That's why I keep talking about CO2. Well, lower CO2 prices are critical. And here is a rate of return calculation, and let's say you need to get to be 20% without G&A in order to sanction a project. So you're looking at that orange curve. You would need, at $50 a barrel, you're going to need to get down to about 80 cents an MCF to get this project up to a 20% rate of return. And, you got to get that 20% because you got to pay the G&A, and look at the G&A. If you include it, it's under 15. And then this is all before taxes. So you got to have enough money to pay taxes. So you might think, gosh, why don't I get a 20% rate of return at home? Well, you got to have overhead and you got to pay taxes. And when you get done with that, you're down to 10%. So lower CO2 prices are absolutely critical to get these projects done, especially on lower oil prices. And and we're 45Q is coming to the rescue. And it could supply a $35 a ton tax incentive. And that's actually 3.5% of oil price. And so, that's larger than the oil price, I assume. So you'd actually have a negative CO2 price. But the delivered price of the CO2 might increase. And that would be because, at least in West Texas, most of the CO2 that's brought to market comes from an underground source, which is much cheaper than capturing it out of a vent stack or out of the atmosphere. But 45Q could be the answer to a lot of people's prayers, and it would move people toward using anthropogenic CO2. Now, I believe I need to hand this over to Al, or I'll answer questions. I don't know which way you want to
Yeah,
go.
we'll take a few questions really quick. If anyone wants to raise their hand just on this section right now. Again, for attendees, that's the button at the very bottom middle of your screen. It says raise hand if you have any quick questions. We'll take one or two right now.
Hey, I have a question. This is
Yeah, okay.
Lanny. Yes, Chuck, okay, in the 45Q situation, would you, is it possible that we could sequester more CO2 than what the net utilization factor would be?
Well,
So we get more credits.
yeah, if the price of CO2 is lower, then you'd go longer, so it changes some of the economics. You're always saying, hey, how much is this profitable? Is it profitable? Is it profitable? And if you reduce the largest cost input, you're going to use more of it.
Awesome. Well, there's no other questions coming in, so we'll oh no, we do have some questions. Let's see if we can take these right now. Let's see, William, you should be able to talk now.
Yeah, Chuck, one quick question is, how do you see the trajectory in terms of oil and gas industry moving away from the natural CO2 to anthropogenic CO2?
I see it as it's a matter of cost. Now, in some cases, the CO2 sources are petering out. The Sheep Mountain no longer produces much, if anything. Bravo Dome is, it's not, maybe not its last legs, but it's certainly not as productive as it once was. Jackson Dome, similarly. And so I think you have a desire to move to another type of source. There's also a societal desire, but it's all going to come down to someone penciling in a number. And what we're going to see later is a lot of the cost, a lot of the places where you can capture CO2 costs a lot of money, and maybe more than 45Q can provide. So, I don't know if does that.
Yeah, okay, thanks. I appreciate that.
Awesome. Well, thanks, William, for the question. So now we're going to turn it over to Al Collins, and I'll invite Lanny on as well to turn on your video and introduce Al.
Okay,
Lanny,
can
are
you
you
hear
here
me?
with-
Can you hear me?
Yes, I can.
Yes, it's a pleasure. It's a pleasure to here. Let me. Yes, it is a pleasure to introduce Al from Oxy. Al Collins is the Vice President of Policy and Engagement at Houston-based Oxy Low Carbon Venture in a division of Occidental, an international oil and gas exploration and production and chemical company. Oxy is one of the largest oil and gas companies in the U.S. based on equity market capitalization and the world's largest use of carbon dioxide to enhance oil recovery. Over the past 36 years, Mr. Collins has held a variety of positions in the environmental policy, engineering, and management fields. His experience spans air, water, hazardous waste, toxic, and Superfund issues, both on behalf of regulators and those being regulated. At Occidental, Mr. Collins is involved in a variety of issues, including hydraulic fracturing and endangered species, restoration and remediation operations, toxic and EOR using CO2. Mr. Collins was very involved in Occidental's development of the first U.S. approved plan for qualifying the amount of CO2 geological stored during EOR. Prior to joining Oxy in 2000, Mr. Collins served as 2 years as Vice President of Regulatory Affairs of National Environmental Strategies, representing clients on environmental and small business issues. From 1985 to the end of 1997, he worked at the U.S. Environmental Production Agency, where he developed regulations and policies related to waste, toxic, and water. Mr. Collins holds a degree in chemical engineering and economics from North Carolina State University. Al, it's my pleasure to turn it over to you right now. Thank you very much.
Thank you. Can everyone hear me?
We got you clear.
Faye, can you hear me?
Yeah, I can hear you loud and clear, Al.
Okay, great. Awesome.
You just
You're
got
gonna
to
bring
keep
up-
flipping through there. Yeah, I think you have control now, and you should be able to just keep clicking through, and it'll bring your slide up in a second.
Gotcha. All right.
There you go.
There we Well, Lanny, thank you for the introduction. I'm going to talk about the 45Q tax credit. And but first, I wanted to just give a little bit of background on Oxy's enhanced oil recovery operations and our use of CO2. We are the world's largest user of CO2. The point that Chuck made earlier, I think, is really important to reinforce, which is most of the CO2 that Occidental uses is naturally occurring CO2. But we inject about 50 or 2.6 billion cubic feet of CO2 a day. That works out to be about 50 million metric tons per year. Of that, about 20 million metric tons is sequestered. So I like to say we have the ability to sequester 20 million metric tons of anthrop CO2 as soon as we can get our hands on it. Just to give you some idea about scale, that equals the annual emissions of about 4 million passenger vehicles. So it's quite a bit of CO2, and we inject it to enhance our oil recovery. And we recover over 150,000 extra barrels of oil every day because of the CO2. We've got 34 floods in the Permian Basin and control about 2,500 miles of the CO2 pipeline. So about a little bit less than half the pipeline we either own or operate. So let's talk about 45Q. 45Q refers to a tax provision in the tax code that's designed to incentivize carbon capture and in particular the technology needed to capture CO2 from emissions. It's a production tax credit, which means the more CO2 you capture and sequester, the more you qualify for the tax credit. And the credit was originally enacted in 2008. In 2009, Congress made a technical correction to it, which had to do about the accounting of 45Q under utilizing enhanced oil recovery. And then it was expanded in 2018, and that's what I want to talk about now. So the original expansion was introduced, it was bipartisan and introduced by Senators Heitkamp and Barrasso and Capito and Senator Whitehouse. And it became part of the Bipartisan Budget Act, which was enacted in February of 2018. And it changed some key provisions of the original 45Q, which actually is still in place for operations that were not, did not qualify after the enactment. So if you qualified under the old program, you can still take advantage of it until the program expires, which is based on a threshold of 75 million metric tons. And I think we're fairly close to reaching that cap. So let's talk about the changes to 45Q that happened in 2018. So the first and most important is it increased the credit value. Originally, the credit value was $10 per ton for sequestration that happened in conjunction with enhanced oil recovery, and $15 per ton for sequestration outside of the OR. That bumped up to $35 per ton for EOR and other types of utilization, which I'll talk to it in just a minute, and $50 per ton for sequestration outside of the OR. The second important change is it allowed utilization beyond enhanced oil recovery. So Chuck mentioned the use of CO2 to make plastics and cement and those types of things, fuels. Those now qualify as sequestration under 45Q. The third thing is that it lifted that 75 million ton cap that I talked about and goes to a credit for 12 years once a project is brought into service. So it's a lot easier to bank on when you're using the tax credits to invest a project. We can talk about that a little bit later. It expanded the threshold eligibilities. In the next slide, I'll go into detail on that. And then one of the most important things about financing projects with the tax credit is it allowed the transferability of the credits to other parties. So let's see. All right, I'm trying to advance the slide.
You may just have to click back on the screen. If not,
All
Amy
right.
can hopefully get you forward. There we go.
I did it the wrong way, and here we go. All right, let's talk about the eligibility requirements. Under the old 45Q, you had to capture at least 500,000 metric tons from each project, which meant that only very large electric utilities qualified and maybe certain refineries. Under the new, the updated 45Q, projects that capture at least 25,000 tons that are using it for beneficial utilization other than EOR qualify. Projects that industrial facilities that capture at least 100,000 metric tons qualify. And so that means that operations like larger ethanol refineries, certain energy intensive operations like maybe a cement operation or iron and steel may qualify. So it lowered that threshold to make other types of projects available. I mentioned earlier that the projects that come into service can qualify for the tax credit for 12 years. And another important change that was made was that the begin construction definition was extended a little bit beyond what was typical for projects under IRS tax credits. So they increased it from 4 to 6 years, and which means that if you begin construction before January 1st, 2024, that's when the actual program expires. So if you begin construction before that date, you have 6 years to bring your project into service. And if you do that, then you qualify for 12 years of the tax credit. So this is really important. And if you leave today with one takeaway from my presentation, I want you to understand that 45Q is not a tax credit for the oil and gas industry. I think it's been associated with oil and gas because sequestering CO2 in conjunction with EOR operations is a proven approach. It's probably one of the lower cost approaches right now. So I think that's where the oil and gas industry and 45Q have gotten connected, but it's not an oil and gas tax credit. And I think that's important with policymakers because they need to understand that that this is for incentivizing the capture project. So the 45Q credit actually belongs to the capture project. Let me see. In order to get the credit, though, the capture project needs to either sequester the CO2 or contract with a sequesterer to determine how much 45Q they qualify for. And let's talk a minute about sequestering CO2 and how that's quantified. Congress tasked the IRS with determining what sequestration was for the purposes of 45Q. IRS asked for EPA's help and relied upon the EPA regulations for determining the quantity of CO2 that's securely stored. And there's a mechanism under EPA's rules under the USC program, which Chuck talked about earlier, which is called the MRV program. And these are plans, monitoring, reporting, and verification plans that when implemented determine the mechanism for quantifying the amount of CO2 that is securely stored. And it's reported annually in EPA's greenhouse gas reporting website. So the plans that have been approved by EPA are on their website, and the reporting of everyone taking advantage of those plans are available for anyone to go and look and see. So there's a lot of transparency about this program, which is something that appeals to Oxy quite a bit. We do have 2 of these plans that have been approved. I suspect we'll probably be doing more of them in the future. It's important to note that after the enactment of the Future Act in 2018, the IRS started developing rules to implement the changes to the 45Q program. And one of the things that they're currently, that they've proposed and the comment period has closed, is whether or not there should be other approaches for determining the amount of CO2 that's sequestered. So they have proposed an alternative mechanism for this, which relies upon an ISO standard for determining the amount of CO2 that is stored during enhanced oil recovery. And that the way the IRS proposed this is that you'd follow the ISO standard, develop a MRV-like plan, although it has a different name, have that approved by a third party, and you would use that approach to determine the amount of CO2 you claim, and then every year you would claim the credits for the amount stored in the previous year. I've got a few more minutes, and I thought I would talk a little bit about what Oxy's done with Oxy Low Carbon Ventures and how 45Q has helped enable us to create a business around sequestration. And since I've got a few more minutes, I'll just run through these just to give you an idea about how businesses may take advantage of 45Q to help incentivize more sequestration. So we started Low Carbon Ventures in 2018, and the purpose was twofold: to capture industrial CO2 to utilize in our enhanced oil recovery. So we want to transition away from the naturally occurring CO2 and use more anthro CO2. And then, so we're going to do that through developing projects with emitters where we work with them to capture the CO2, and then we take it to sequester it either as part of our EO operations or just in outside of enhanced oil recovery, just in straight sequestration. We will also be developing projects for harvesting CO2 from the atmosphere. This is called direct air capture. And we've announced our first project, and I'll cover that in just a second. So let's see. The first project we announced after the enactment of 45Q was working with a company called White Energy, which is an ethanol refiner and has two facilities that are very close to Oxy's operations in Texas. So there's pipeline infrastructure near these. Ethanol is interesting because it produces almost a pure CO2 off stream. So the capture is fairly straightforward. So we will capture CO2 from White Energy's facilities, put that into the pipeline system in the Permian, and send that to be sequestered as part of our EOR operations. The second thing is the carbon engineering project that I mentioned, which will be built somewhere in West Texas, capture about 1 million tons a year from the atmosphere, and we'll utilize that in our enhanced oil recovery operations too. Next thing is another interesting project we have announced, which is about utilizing CO2 in the way outside of EOR, which is Cemvita Factory, which makes a bioethylene, and we'll be injecting anthro CO2 into that project, making a bioethylene product. And OxyChem is already a producer of VCM and ethylene. So it's kind of a natural outgrowth of our OxyChem business. And this is a way of taking advantage of 45Q outside of straight sequestration and EOR. Let's see. So we've also started a company called Sequest, which will be just a dedicated company to sequestration outside of enhanced oil recovery. We'll be developing what we're calling sequestration hubs, where companies that are emitters that are located in close proximity can take advantage of shared infrastructure to help lower the sequestration cost and have availability of 45Q at $50 a ton. The last is our Clean Campus idea, which it's linking all the technologies together, where we build direct air capture facilities where the CO2 can either be sequestered with EOR or without EOR. The oil produced from EOR, of course, has a much lower carbon intensity, which Chuck covered. We believe that it's absolutely possible today to produce a barrel of oil that has that's either carbon negative or carbon neutral, looking at the scope 1, 2, and 3 emissions from that barrel of oil. We think there's an absolute market for a zero carbon oil for hard to decarbonize industries like shipping, airlines, and long haul trucking, where batteries are not a good solution right now. And we anticipate the direct air capture projects to be powered with zero carbon power, be it wind or solar, or power from another investment that Oxy's made in Net Power, which produces a zero carbon power utilizing natural gas and a pure stream of CO2, which we would actually use and sequester in our system. So I hope that piques your interest a bit about what Oxy is doing. We have a website called oxylowcarbon.com, which explains these projects and other services that we're offering. And we appreciate the opportunity to talk about 45Q. We think it is a real game changer and are very glad to participate in it. So thanks for the opportunity today, and thank you, Lainey.
Thanks, Al. So we're going to hand it back over to Chuck now. There you are, Chuck.
Yep. Okay.
And so I think Amy should be able to pass the remote back to you, and we'll continue on. We do have a short break coming up in about 15 minutes before wrapping things up. So
Okay.
I'll let you take it away, Chuck. Thanks.
Well, Al really led into this next thing, other storage options. And we'll take a look at gas fields, saline reservoirs, and coal beds. And here's a nice picture from the USGS. We spent most of the day talking about EOR, but there's other options. And like oil fields, gas fields have the advantage of a known seal and a well-characterized reservoir. They've been studied for development, and the seal has held gas in place for millions of years. But unfortunately, like oil fields, gas fields are relatively scarce. I mean, relatively scarce. There are a lot of them, but they're not everywhere. As opposed to saline reservoirs, they are almost everywhere. They have a large total capacity. But no fluids have been extracted prior to CO2 injection. And so the calculations are made, and it says only 1 to 4% of the reservoir can be filled with CO2. And really here they are of unknown, they're poorly characterized with unknown seal effectiveness. I think you could, with a lot of study, you could figure it out, but on day one, you don't know much. Finally, there's unminable coal beds, and there's potential methane recovery that could offset the cost. And then the question always is, what's truly unminable? And if it's unminable, then you're back to having a poorly characterized resource. At this point, I'd like to talk a little bit about timescales and permanence, and what are we trying, how do we think this is really going to work? And there we go. And here's a couple plots that sort of show the same thing or similar things. They're from the IPCC report, carbon dioxide capture and storage. And what you find is physical trapping dominates the early years, and that is you put the CO2 in place, you've got a seal at the top. Even if CO2 rises, there's a seal, and physically there's a physical barrier to later, in terms of tens to hundreds of years, residual, and that's relative permeability. We talked about that earlier. Residual trapping and solubility trapping dominates, and solubility trapping occurs when the CO2 dissolves into the water to make it denser, and then the dense water drops. I mean, before you had CO2 is lighter, less dense, it's going to rise, but when it goes into the water, it's heavier and it starts to sink. And finally, over thousands to tens of thousands of years, the CO2 precipitates into minerals. So let's have look at some examples of each one of these. The first is the Insala field. It's a gas field in Algeria, and CO2 is injected down dip, and it's expected to migrate up dip toward the production wells. The injection started in 2004, and it stopped in 2011. And CO2 from several gas fields was all brought together into a central gas processing facilities. Then the CO2 that would have been vented was compressed and transported and stored in this 1.9 kilometer deep Kretschbach field. 1.9, it's 2 miles, a little over 10,000 feet, or about 10,000 feet. And there has been a lot of study on this. This is, I think, the first one that was done in a gas field. So there's lots of interest. They had a diverse portfolio of geophysical and geochemical methods, time-lapse seismic, microseismic, wellhead samplings using CO2 gas tracers, downhole logging, core analysis. And the thing I thought was most interesting was this INSAR data. And this is out in Algeria, and there's nothing growing. It's a perfect place to use it. It's satellite data that where you get to see how much the Earth deforms, and they could see the CO2 going in. There's a deformation. When it moves, there's a deformation. And so that was kind of interesting. The cost of doing all this was $100 million, since it was 3.8 million tons of CO2, that's $26 a ton. Well, that would work if you had a $35. Well, this is actually not even EOR. This is if someone's giving you $50 a ton, someone's giving someone $50 a ton, you could do this. The next one here is a saline reservoir. It's the Sleipner field, and this is offshore Norway. This is another very famous field in the CO2 storage world. The injection began in 1996. It was the world's first commercial storage project. And every year about 1 million tons was injected. The natural gas from Sleipner West field, it contained about 9% CO2, and they were venting it in the atmosphere. And because they had to meet export specifications, and for this part of Europe, it was 2.5%. They were venting it. In 1991, the Norwegian authorities introduced a CO2 emissions tax in order to reduce the greenhouse gas emissions. And Statoil now is Equinor. They put about $100 million to compress and reinject the CO2. And it apparently worked. I was kind of interesting. This was the time I was wandering around. I had a purpose. I had a purpose. Something just happened. Am I still there?
Yeah, you're still good, Chuck.
There.
Your slides are up and you're good.
Okay. Anyway, I went there and I found out that there's some people in the tax group and the government of Norway were kind of miffed that Statoil had started to sequester the CO2 because they weren't paying the tax anymore. I guess they'd gotten used to receiving the money. Anyway, the behaviors of the CO2 in the sandstone has been mapped. There are lots of things that have been published. For some reason, I didn't turn my phone off, and yeah, thanks. Somehow it affects my screen. All right, the last thing here is coal bed methane. And coal contains these permeable fractures called cleats, and between the cleats, there's solid coal, and it's got micropores, and coal can adsorb many gases. And there's this absorption isotherms I've pushed up here in this plot. And you can see that at various pressures, there's more CO2 can absorb onto the coal than the methane or nitrogen. And this is how coal bed methane works. If you just let's say the methane's in place and you depressure the reservoir, the reservoir can hold on to less CO or less methane as you drop the pressure. And so when you drop the pressure, the methane comes off and you can produce it. Well, if you inject CO2, it turns out that it displaces the methane because the CO2 preferentially absorbs onto the sources, onto the rock, and you can sequester it there as long as you keep the pressure up. And you actually produce a little bit of methane, but unfortunately the CO2 swells the coal, which makes the whole thing a little bit harder to manage. But you can put CO2 into in coal beds. Okay, this is a 10, I guess we're up to a 10-minute break. I was just getting going.
Yeah, exactly. We actually have a few minutes left over. So if there's any questions from the attendees for Al, Collins, or Chuck on their recent sections, please raise your hand again for attendees. That's at the middle bottom of your screen, says raise hand. We'd love to take some questions before getting into our break. See, we're right on time, so we do have a second to wait if there's any questions mulling over there. We will be trying to come back and start again. We do have a question coming up, but we will be trying to start back up just for everyone's information at 1:45 Central. Nick, you should be able to speak now and ask your question.
Yes, appreciate the talk so far. I had a quick question on the time frame of the 45Q credits, the 12-year time frame, and want to get your guys' thoughts on just.
Lost you.
Oh, was
Could you
sufficient.
repeat that last end, Nick?
Yes, sorry about that. I just wanted to touch base real quick on the 12-year time frame for the 45Q and get your guys' thoughts on if you thought that was a sufficient time frame for generating interest in some of the longer term or larger scale sequestration projects that may timeframes may extend outside of that 12-year window, if you will.
So I think that would be a question for Al, if I can get him back on here. Unless you have anything to add to that, Chuck, not to.
12 years is a long time, but your point's well taken. If some of these projects, they may go on for many more than 12 years. And especially ones where there's no economics. If you're putting it into a saline reservoir, when the tax credit's done, you're done. Now, you may have filled up that spot in 12 years, right? And then you may move on. So if it's a saline reservoir, maybe you'll manage that. But I think if you had something going on, someone could petition the government and they might say, okay.
Can't seem to get Al on yet. So Nick, if you want to ask that question at the end, feel free if you want more information from Al as well. Can't seem to get him on right now. Any other questions? We got probably time for one more question if there's anything else out there. All right, well, thank you all. We're gonna be back here in 10 minutes. So at 1:45 Central Time, we'll pick it back up and wrap things up. Thank you. Alrighty, so we're just right on time, so we'll keep moving along. I'll hand it back to you, Chuck.
All right,
and
thank
can
you very
continue.
much.
Yep.
Okay. We're rapidly closing in on the end of the day. Capture and transportation is the second to last chapter, and really the last one that has very many slides at all. In order to capture CO2, you need to know where to go to look for it. And here are the sources of greenhouse gas emissions in the United States from the EPA website. In 2018, US greenhouse gas emissions were 6.7 million. That's not tons. Well, our problem is over if that's right. Gigatons of CO2. Excuse me. And the most of it comes from transportation. It's 28.2%, and they're primary from burning fossil fuels for our cars, trucks, ships, planes, that sort of thing. And over 90% of fuel that's used for transportation is petroleum based. It's basically gasoline and diesel. Electricity production is 26.9% of US emissions. It's the second largest share, and about 60%, which we'll see, 63% of the electricity comes from burning fossil fuels, and that's 63% of that electricity is what shows up on this pie chart. Industry is 22%. This is primarily comes from burning fossil fuels for energy, as well as greenhouse gas emissions from certain chemical reactions. I mean, if you're going to make cement or something, that's what it is. And finally, a commercial and residential. This is for businesses and homes, and it's primarily where we burn gas or something for heat. And then agriculture is 9.9%. And that's from livestock like cows, agricultural soils, and rice production actually has a fair amount of emissions. Now, the land use and forestry that's not shown on here is a negative 11.6%. And they act as a sink, and they manage forests and other lands are a net sink. So they are a help. Now, electricity is 27%, and we're going to focus on that because it's very difficult to capture CO2 from a moving vehicle. And so you're really looking at electricity sources and then some of the industrial sources. So let's look at US electrical generation. And the largest amount of electricity generation right now is natural gas at 38%. Next down is coal is 23%, way down, but it's the second largest. And then you go over to nuclear and the non-hydro renewable and the hydro, and then the other is 1%. So the natural gas and the coal is where you get where we get our CO2 or greenhouse gas emissions. And if you look at the chart on the right, you see that coal is it's the proportion of power that we get from coal has dropped dramatically from about 2005 until today. And that's primarily due to natural gas increasing. It's also due to the non-hydro renewable, but the natural gas fired generators took a lot out of coal. Well, if we've got the emissions from the power plants, and I've laid out several of them types here, we've got the pulverized coal-fired plant with subcritical steam cycle. We'll talk about that in a second. Then the pulverized coal plant with supercritical. You've got an IGCC plant. And finally, a natural gas combined cycle plant. So finally, I put nuclear in this chart. Well, the source was Bechtel. Nuclear and hydro and the other renewables are all zero. Pulverized coal-fired generation plants use finely crushed coal that's fed into a boiler that's burned to create heat. And the heat produces steam that uses to spin one or more turbines. And supercritical or subcritical, here comes back again, this phase behavior refers to the temperature and pressure conditions of boilers. A supercritical steam generator operates at such a high pressure that actual boiling ceases to occur, and the boiler has no water steam separation. So actually you're in the dense phase, like CO2. So and supercritical plants use higher pressure and temperatures, and they boost the efficiency to 40% or more. And the subcritical steam, it operates below the critical pressure of water, which is 3,200 psi. So when you increase the temperature, you actually get a dew point. And those new plants are around 37% efficient. So if you're a little more efficient, you have a little less CO2 is emitted per megawatt, megawatt hour. Then you have these IGCC plants, and that's integrated gasification combined cycle plant. And it's fundamentally different than pulverized coal. In an IGCC process, the coal is heated under pressure to create a methane-rich gas, which after cleaning is used in the combined cycle plant to generate electricity. And of interest for us is pure CO2 is a byproduct, or nearly pure CO2 is a byproduct of an IGCC plant. So there you can capture it like at the Dakota gasification plant at a price that an oil field can pay, and that's happening where they take that CO2 up to Canada. A natural gas combined cycle plant uses natural gas as a fuel, and a combined cycle means you take 2 bites of the apple, you use you have a turbine that runs on the expanding gases when you burn something, and then you have a bunch of hot gas, and you use that hot gas to boil water to turn another turbine, and then you get more electricity coming out of it. So you can see here with this CO2 emissions in kilograms per megawatt hour that a natural gas combined cycle plant is about half of the regular pulverized coal plants. So that's why when you move from coal to natural gas, you drop your CO2 or greenhouse gas emissions in half. And that's a lot of what's been happening in the United States in the last 15 years. Another thing to consider is the CO2 content in the flue gas. And if it's coal-fired, it's 13%, oil-fired is 8%. In the United States, the oil-fired plants are pretty much gone, unless you're on an island or you're in Alaska. So you've got coal-fired at 13% of CO2 and the emissions, and gas-fired 3%. That's why gas is better. But if you're looking at trying to sequester CO2, you want to look at your coal plants, because at least it's 13% CO2. So if you're trying to capture CO2, you only have to handle, say, 7 to 8 times more of the gas to capture a molecule of CO2, whereas for capturing a molecule of CO2 from a gas-fired plant, you got to build something that's 33 times what you're really interested in. And so that's why the holy grail has always been these coal-fired plants for capture. And then what about these non-power emission sources? And I've shown these various processes up here, the power plants at the top and the world emissions and the percent of world emissions. So when you take a look at this, you see that really what you'd like to address is power plants, although you've got cement plants, refineries, steel mills, ethylene plants, all this other stuff. But the key on much of this is what is the percent CO2 in the gas? And this is only showing processes that have more than 100 sources. And there can be several emission points within each of these sources that have different concentrations of CO2. Because you look at the steel mill at 15%, that's interesting, but it turns out that the blast furnace has a 27% concentration. Refineries is 3 to 13%, but there's if they need hydrogen at the plant, the CO2 content of the gas off of that vessel might be close to 100%, with the exception of the water vapor, which is relatively easy to pull out. Cement kilns can vary between 14 and 33%, but then you've got these ammonia plants and fertilizer plants and things like this that are 100%, and those are the places you really can go to and make a go of all this. Now, what's the capture methods? Well, there's several. You've got post-combustion, pre-combustion, and oxy-fuel. And post-combustion, you just take a conventional plant, you add CO2 capture facilities to it. It might be some amines. You got to cool the CO2 or the flue gas to some temperature that makes the process work. You run it through an amine or something like that. The amine captures the CO2, then you take the CO2 off or the amine off, you heat it, and that kind of boils off the CO2. And now you have pure CO2 with maybe some water or some in it, which you can then run through a glycol and you can get dry CO2. You just are hooking something on at the end of a regular process. In pre-combustion, this is this IGCC plant. You're using a chemical shift reaction to create, maybe carbon monoxide, and you create hydrogen, and those are all things that you can burn. And then what comes out of that, it turns out, is nearly pure CO2. And that is easy to capture, but by gosh, it costs a lot more to build an IGCC plant than a regular coal plant. And you would never do that. You would never do that except as some path toward capturing CO2, or if you needed hydrogen for some reason. Then you have these oxy-based oxy-fuel combustion. And what oxy-fuel combustion is you realize that one of your problems with post-combustion capture is you have all this nitrogen that has just gone all the way through the system, and it's in the flue gas. And so you got this CO2, but most of the rest of everything is nitrogen. You have to deal with the nitrogen. It's just, you make everything bigger. Well, what if, and more hard, and what if you could pull that nitrogen out ahead of time? Now you burn whatever it is to burn with pure oxygen. And what that means is that what comes out the other side is pure CO2 or pure CO2 and water. And those are easy to handle, and you spend your money up front. And it's a real nice process. The problem is when you burn in the presence of pure oxygen, it gets really hot. It gets so hot that the metals start to deform, or it's harder to machine the metals because they're different kinds. Anyway, that's another way you can do it. Pull the nitrogen out, or pull the nitrogen out at the beginning. And then you got your industrial processes, and those are some combination of all of, like post combustion generally. So that's your capture methods. And the question is, what the heck's the cost? And this is where it all starts to fall apart so far. And according to a 2017 Forbes article, which Forbes Online, they used data from the US EIA and NETL, National Energy Technology Lab, and they found out that capturing CO2 from a new supercritical coal plant, that was the best of the pulverized coal plants, adds $59 per megawatt hour to the energy costs. And I was able to go find the source documents, and from that information was able to back calculate that the CO2 capture cost there was $70.70 a ton, $3.70 an MCF. And then for grins, they told us that the tax credits for winds and solar were $20 to $25 per megawatt hour. I'd put this on, if I'd made the slide later, I would have said, well, that compares to $35 per megawatt hour for the 45Q. But what it is, you still can't capture the CO2 even with, say, with 45Q at a price an oil field is willing to pay. You're not quite there. And like capturing CO2 from natural gas likely costs more because it only has 3% CO2 in it. So that's tough. The cost to capture, dehydrate and compress pure CO2 from 0 to 2000 PSI G is about $11 a ton or 60 cents an MCF. It could be 80, somewhere in there. So if you have a fertilizer plant, if you have another type of source of nearly pure CO2, like in the Valverde Basin, you can capture it at a price that you can get it to an oil field. And Al talked a little earlier about, I think it was White Star, that there was a plant, I believe it was in northern Panhandle of Texas. And I looked at that a few years ago and actually talked to those people. And we could not capture that CO2 and get it into the pipeline system at a price anybody would pay. But with 45Q, and the problem was the distance. At 45Q, that made that work. So 45Q is going to make some things work. And so the principle is, if you have nearly pure CO2, you can capture at a price that an oil field can pay if you're close enough. And if you have 45Q, you can move the CO2 further. And I have a picture here, and this is really of a disaster, economic disaster. This is Southern Company's Kemper County IGCC plant. We talked about the IGCC plants. It was supposed to cost $2.2 billion. As of 2017, the completion cost rose to $7.3 billion. And they were going to have this IGCC plant. They had pre-sold the CO2 to some to some oil fields, and they were going to sequester the CO2 in the oil fields. It's all going to be beautiful. And the cost got out of control. And then when they turned it on, it didn't work. And that's when they threw their hands up and they converted what was left or salvageable. Then they switched to natural gas. And at the time of this debacle, it caused power costs in the county to go up 30%. And you think, I think they just said, I don't know why they allowed that, but perhaps they wouldn't have had any power if they didn't make people pay a little bit more. So the cost is a real darned issue. And the last thing I always want to talk about, CO2 transportation. This has been practiced for almost 50 years, CO2 transportation. It's regulated under PHMSA, under Part 195 for liquid pipelines. You think CO2 would be a gas, it is at atmospheric pressure. You put it into the dense phase, it's really a liquid. And so it's regulated with liquid pipelines. They operate at some higher pressures than, say, gas pipelines. Got some specs here I've provided. We've talked about why you have some of these, like the CO2 spec, nitrogen, hydrocarbons. This is all comes from minimum miscibility pressure calculations. You got water, you don't want to have corrosion. If you keep it under 30 pounds per million cubic feet, you will never see corrosion in a pipe. Oxygen's about corrosion. H2S is safety. Glycol, just keep it down so the glycol doesn't show up in your instruments. And temperature has to do with material. So, these are the general quality specs in the US generally. I pulled out some transportation costs from this IPCC report in 2005, and I think I gave this to them in 2004, and somehow it all got into this report. But I updated them for inflation, and the top curve here just says, hey, the farther you take something, the more it costs. Well, duh. But anyway, I think those are a little bit high. But then there's the cost to transport CO2, 150 miles. And what you see here is this in mass flow rate in terms of million tons of CO2 per year. Once you get it to about 50 million tons a year, you kind of, that's as big as you need to get. After that, you've achieved your economies of scale. So transporting the CO2, it's easy to do, but there's a cost there. So, and this is rather short. This is kind of fitting it all together, and it's an explanation of how we are where we are today. And 45Q is going to help, and the LCFS, that's the low carbon fuel standards for California, for some cases can really help. But let me just go into this. This is an interesting curve that I pulled out and later realized, oh my gosh, you've managed to save the one that's in terms of euros per ton, but I don't think it makes any difference. This is rather old. It's about 2009, and McKinsey and company put this together. And this is the abatement potential for various carbon mitigation options. And the abatement cost is in the y-axis from negative 80 euros per ton to positive 80 euros. And what's a euro? I mean, it's like 10, 20% more than a dollar. And the various technologies are rayed out on the x-axis with the mitigation potential shown by its width. And what I've done here is, well, I've highlighted the CCS or CCUS activities. And the activities to the left are various options like energy efficiency gains and conservation that actually pay for themselves. So, I mean, these are things like changing the light bulbs, that sort of stuff. It really does pay for itself. People ought to be doing or nudged to do them or whatever. But you can abate quite a bit of CO2 at native costs. And one of the things you see is that, even if you combine EOR with CCS, you're generally negative. You're still negative. And that's because of the capture costs. And there's got to be something that bridges that cost. 45Q goes a long way to getting nearly pure CO2 sources into the ground. An interesting one is this big fat option. Let me just think that's one right there. That's the nuclear option. And that would be preferred to, gas plant retrofits or coal plant retrofits. And McKinsey has come out with this at different times, and nuclear options was at that one was actually slightly positive, who knows. But unfortunately, CCS has unfavorable economics absent unless you have a source of nearly pure CO2. And now we're coming up on the last slide, but we know, or I know, that CO2 is going to stay in the ground. I have no question that this is going to work. We know CCUS can work economically in some cases, and these cases I'm going to show you are, we're without any tax help. The Val Verde natural gas CO2 separation plants in the 1970s, that was where it all started. So it started with CCUS. And then the Dakota gasification plant supplies Canadian floods. Now, I'm not sure anyone's signing up to build another IGCC plant, but if you did, you're beyond the way. The CVR refinery in Coffeyville supplies, in Coffeyville, Kansas, supplies CO2 to the Burbank field in Oklahoma. And 40 million cubic feet a day, every day, goes down into Oklahoma and gets sequestered. And it's net negative oil, I think. And then you got ethanol plants wherever they are. They can supply, there's ethanol or is it fertilizer? Gosh, in Michigan. So we know what works is nearly pure CO2 sources near oil fields that only require dehydration and compression. The 45Q goes a long way to help transport that CO2 farther. But this is my opinion, is that if we're going to expand CCUS or CCS beyond the nearly pure sources, there's got to be more incentives that society provides, or there's a technological breakthrough like direct air capture. It's got to occur. And I thought that was nutty. I thought that was crazy. And I did some calculations, and I now not sure it works economically, but I'm sure more interested, and Oxy's going to build something. And so they're not fools. I think this is on the edge. I think they're on the edge. But after you build one, the second one gets better and better. You learn more. So this direct air capture might be the breakthrough you need, because a lot of times the CO2 that's being emitted isn't anywhere near where you can put it in the ground. And that's, so more to come on this. I think you're going to see a lot more of it, but it's going to need some help. So that's the end for me. I'm ready to take questions, hand it back to our sponsors. And
Thanks so much, Chuck.
Talk and go for
That
it.
was awesome. Yeah, so we'll take questions. We already have some questions coming in right now with raised hands for you and Al. We'll try and get questions for Al first if we can, but there's only one hand raised at the moment, so I'll take this. Oh, he just put his hand down. Well, John, if you put your hand back up, there you are. John, you should be able to talk now.
Hey, thank you. The question actually wasn't for Al, but it was just a point of clarification regarding the Dakota gasification plant. It is not actually an IGCC plant. It is a plant that produces a synthetic natural gas that's put into the natural gas system. So it doesn't produce power. So that's just a point of clarification.
Thanks. Well, I'll fix, I don't know, I'll try and fix my slides.
Yeah, the curious thing with it, there's actually an adjacent coal-fired facility that provides it with power. So it's exactly not an IGCC plant.
Okay.
Thank you, John. Any other questions from the attendees? Just a reminder, the button to raise your hand is right there at the middle of your screen at the bottom. William, you should have the floor now.
Yeah, so this question goes to Al. Listening to Chuck, I'm curious to know what is the motivation for Oxy, to really move in this bold step to go into this net carbon negative, based on all the economics that Chuck has been talking about.
Well, I appreciated Chuck's presentation. I think it was Had a lot of a lot of great information. Obviously, I can't discuss the financials of our business decision, but I can say that getting into sequestration beyond EOR, getting into carbon capture is just a very logical outgrowth of the experience that we've gained over the last 40 years of separating CO2, compressing CO2, injecting CO2, transporting CO2, and recycling CO2. So it's the question in my mind is, if not Oxy, then who? So we really should be the first mover there. And I do think what Chuck pointed out at the end of his presentation about each project makes the following project, more economic, more efficient, more easily deployed. So I can't discuss the economics, but we're in it to make money, and I encourage you to watch whether or not we're successful. I feel very bullish about it. And again, I think it's a logical outgrowth of everything we've been doing the last 40 years. And thank you for the question, William.
Let's see. We have another question up here. But I'm going to ask if Ramon is still on the line. You had a question earlier for Al, I believe. So if you want to raise your hand and ask that again, we can get to that. But right now, Ali, you have the floor.
Yeah, great workshop. Thank you for everything you guys are doing, getting this out to us. The question I had is, Chuck, you showed earlier that the number 3 CO2 generation was from refineries. And related to that, I had 2 questions. One is, do you know of any refinery sequestration projects? And how does that map into your CCS economics slide you showed with those bars in euros?
Yeah, well, there's been several examples of CO2 being captured from some refineries. And the first ones were down in Trinidad, and they took the CO2 from some part of the refinery, and they captured it and they put it into 4 fields. The other one is an ongoing one. It's a fair size, is the CVR refinery in Coffeyville, Kansas, and Perdure is the name of the company right now, has a capture facility that they installed at the refinery. And so my guess is, but I don't know, but my guess is it's nearly pure CO2 that's coming off something that's making hydrogen, and that they need at the plant to upgrade their, to make whatever they're making at the refinery. And so there's some examples of going to a refinery and grabbing the CO2 and taking it to an oil field. Is that the question?
Yeah, well, the question was related to the economics.
Well, okay. I think what's happening, but I don't know, but I think what's happening is that there are nearly pure sources of CO2. I mean, 100% CO2 or nearly 100% CO2. And the only thing that's the major thing that's in them that you don't want is water. And so you can run that through a dehydration vessel or set of vessels. And then you can dehydrate it, and then you can compress it. And you can do that at a cost that an oil field can pay. So I think that's what's happening at the refinery. And I don't think by any means they're capturing all of the CO2 that's going up from the refinery.
So the retrofitting is not going to be too expensive, is what you're saying, which is probably the largest cost, right?
Well, yeah, I mean, would be happening right now is CO2 and water vapors going up a stack someplace in the refinery that's coming off of a vessel, and then where you make hydrogen, one of the byproducts is CO2 and water. So that's just being vented off. And what they need is they need some blowers and maybe some cooling equipment, I don't know, to get that to your dehydration facility and your compression facility. So I don't think it's a lot. I think one of your biggest problems is finding space for a pipe in a refinery, or I know from being operating gas plants could be difficult, but I think that's your biggest problem. And so it's probably not a big cost.
Thank you.
Thank you, Ali. We have another question from William. I'll let you take the floor in a second. Will, really quick, just for any questions, I know Al has to drop off here in a second. This email and contact information on the screen for Amy. If you have any questions for Al, you could reach him at al_collins@oxy.com. So that's al_collins@oxy.com. You could send that to Amy or to that email if you can remember that, and we can get those questions to Al for you, just in case you don't get on before Al has to leave. But William, please ask away.
Yeah, so this question is also for Al. I want to know if Oxy is in partnership with any of the DOE carbon safe projects.
We're helping on some of those. Some we're part of the team, and that's mainly being done by Oxy Sequestration Services.
Okay, thank you.
We think that's a great program, and the labs, Nettle, they, in our opinion, they serve a vital and invaluable service by testing the technologies, helping new technologies get off the ground. Big fan of their loan program too. We think if you're interested in this type of business, DOE is a great resource and can be a great partner.
Thank you.
All right, are there any more questions from the attendees? Again, if not, I'll just ask everyone to submit topic ideas or any questions to Amy, and we can forward those on to you. Her contact info is here at the bottom of the screen. And I'll now invite Lanny to have us wrap it up.
I guess I was muted. Now, okay. Yeah. Yeah. First, I want to thank Chuck and Al for the great presentations. They were great. And hopefully we'll see a lot of progress in this area here in the future. We also, I wanted to remind everybody that Chuck will be talking at our November 3rd there at the at our Council of Regulatory Officials meeting on Tuesday, November the 3rd. So you guys can join us there too. And we on the committee, we're going to have we're planning still to have another webinar here on seismic coming up before the end of the year. And we're also working closely with SPE on doing some joint webinars, and that's all to come. And but it's just a lot of good stuff that's going to come here for the regulators. And we just appreciate everything that everybody else is helping us with to make this happen. Adam, do you have anything you want to add to that?
No, I thought that was excellent. I've enjoyed all the hours of it. Your stamina is impressive, and thanks to the audience for sticking it out. I'm looking forward to diving deep on other technical topics of interest to regulators in the coming months.
Great.
This is Amy. I'm going to jump in real quick. Chuck is speaking at the general session on Monday, November 9th.
Oh, I'm
is when
sorry.
Chuck is speaking. But we do have the IOGCC annual conference kicking off with the Council of Regulatory Officials on Tuesday, November 3rd
Yeah,
at 1
that's right.
p.m.
Okay.
So that you can go to our website and register for those, for the CRO resolutions, general session, business session. If you'll go to our website, you can register for those meetings.
Thank you very much, Amy, for correcting me on that. Do we have any other business here? Adam, do you know of any other? I think we're done.
No, people can get their 5 minutes back.
All right. We appreciate everything, guys. Hey, thanks and be safe. And let's make 2021 a lot better than 2020.
Thank you.
Thank you.
Okay. Take care.
All right,
Bye-bye.
take care. Thanks again,
Many
Chuck
thanks.
and Al.
Yeah, in Al.